There is a planet in the sky tonight. You may have seen it without knowing what it was. A faint rust-colored point, steady where the stars flicker, hanging in the dark like a coal that has almost gone out. People have been watching it for thousands of years. They gave it names, they told stories about it. They built whole mythologies around it. Because something about it felt different from the other lights in the sky. Something about it felt close. Tonight we are not going to talk about what Mars is. We are going to talk about what Mars was. Because there is a version of this planet, a much older version, a quieter version, that most people have never thought about. A version that looked almost nothing like the cold, windswept desert we see in photographs today. A version that had clouds, a version that had rivers, a version that may have had mornings. And something took all of that away. Not a collision, not a sudden catastrophe, not a single dramatic moment that changed everything in an afternoon. What happened to Mars happened slowly, over a span of time so enormous that it is nearly impossible to hold in the mind all at once. It happened over hundreds of millions of years. And it happened so quietly, in geological terms, that by the time it was complete, there was no one left to notice. There may never have been anyone to notice. That is the part that sits strangely, if you let it. We live on a planet that is alive in a particular way, a way that feels normal to us because it is all we have ever known. Liquid water covering most of the surface, an atmosphere thick enough to breathe, temperatures that vary, but rarely enough to kill everything at once. A magnetic field wrapping the whole planet like a soft invisible shell, deflecting radiation, protecting the air, keeping the conditions stable enough for life to continue doing what life does. We did not build any of that, we inherited it. And we have inherited it for so long, across so many generations of human beings and the creatures before them and the single-celled organisms before them, that it is very easy to assume this is simply what planets are. Mars is a reminder that it is not. Mars formed around the same time Earth did, from the same swirling disk of gas and dust that surrounded the young sun 4.5 billion years ago. In those early days, Mars was not a dead world. The evidence is written into its rocks, carved into its surface, buried in its minerals. There were river valleys. There were ancient lake beds. There were deltas, places where rivers slowed and spread and dropped their sediment, the same way rivers do on Earth when they meet a larger body of water. There was water, real water, not ice-locked in the polar caps the way it is today, but flowing water, under open skies, on a planet that was warmer and wetter and more complicated than the one we now photograph with our rovers. And then over time, it stopped. The atmosphere thinned, the temperatures dropped. The water retreated, some of it escaping into space, some of it going underground, some of it freezing into the poles. The sky, which may once have been thick and blue-tinged, became almost nothing. The magnetic field, which had once protected everything, went quiet as the planet's interior cooled. And the solar wind, the constant stream of charged particles flowing outward from the sun, stripped away what little remained. What was left was the planet we see today, a desert of iron oxide dust, a thin atmosphere made mostly of carbon dioxide. Temperatures that can drop to minus 80 degrees Celsius on an average night. Silence, except for the wind. Tonight, we are going to walk through that story slowly. We are going to start at the beginning, with the planet Mars as it was, and with how we know what we know. We are going to move through the forces that gave Mars its early warmth, and then through the quiet failures one by one that took that warmth away. We are going to ask, carefully and honestly, whether anything alive might have existed in that ancient window of time, and what we have found and what we have not found, and what the search still means. And at the end, we are going to sit with the question that makes all of this feel personal. Because Mars is not just a dead planet, Mars is a mirror. It is a world that had the ingredients, had the time, had the conditions, and lost them. And somewhere in that story is a quiet question about the world you are lying in right now, with its oceans and its thick air and its invisible magnetic shield keeping the solar wind from tearing the sky apart. How easy is it to hold a world together? The answer, it turns out, is more complicated than most of us have considered. We are not going to rush through it. There is no reason to rush. The universe has been carrying this story for 4 billion years, and it will still be carrying it long after tonight. We have time, so settle in, let the room be quiet. We are going to go back to the beginning of a world that is no longer there. There is something particular about the way humans have always responded to Mars. Not fear, exactly. Not the cold indifference we feel toward most of the other points of light in the sky. Something closer to unease. A vague, persistent sense that this one is different, that this one is worth watching. The ancient Egyptians called it Herdesher, the red one. The Babylonians associated it with Nergal, their god of fire, war, and plague. The Greeks named it after Ares, the god of conflict. The Romans kept that association and gave us the name we still use today. across cultures that had no contact with one another, across thousands of years of independent observation, people looked up at that faint rusty light and arrived at similar conclusions. It felt dangerous. It felt alive in some way that other stars and planets did not. That instinct was not entirely wrong, though not for the reasons those ancient observers imagined. What they were sensing without knowing it was difference. Mars moves differently than the stars. It changes brightness over the course of months, dimming and brightening as it and Earth move along their separate orbits around the Sun. At its closest approach, it becomes one of the brightest objects in the night sky. At its farthest, it fades to something barely worth noticing. No other planet visible to the naked eye varies so dramatically in how it presents itself. And then there is the color, that deep, persistent red-orange, unmistakable once you know what to look for. A color that has no equivalent among the stars. A color that suggests, even at a distance of millions of kilometers, that this object is made of something different. It is made of iron, specifically iron oxide rust. The surface of Mars is covered in fine dust rich in iron minerals that have oxidized over billions of years of exposure to what little atmosphere remains. In a sense, the entire planet is slowly rusting. That is what gives it the color. That is what made it so visible to human eyes long before anyone understood what a planet actually was. For most of human history, Mars was a light. A moving, changing, rust-colored light that appeared and disappeared in the sky on a schedule no one fully understood until the mathematics of orbital mechanics was worked out in the 17th century. Galileo pointed his telescope at it in 1610, but the instrument was too crude to resolve any detail. It looked like a small disk, round, reddish, featureless. He noted its phases but could say little more. As telescopes improved over the following centuries, Mars began to give up small secrets. Dutch astronomer Christian Huygens sketched what appeared to be a large dark triangular feature on its surface in 1659, a marking we now call Syrtis Major, a broad volcanic plain. He also estimated the length of a Martian day, arriving at a figure surprisingly close to our modern measurement, about 24 hours and 37 minutes. A Martian day is almost exactly as long as an Earth day. That coincidence, once known, made Mars feel even closer somehow, even more familiar. By the late 19th century, astronomers were arguing about canals. The Italian astronomer Giovanni Schiaparelli mapped what he called canali on the Martian surface, long, straight features he thought he could detect through his telescope. The Italian word simply means channels and carries no particular implication of construction. But when the term was translated into English as canals, the implication changed entirely. Canals are built. They suggest intelligence. They suggest civilization. The American astronomer Percival Lowell seized on this. Between 1894 and his death in 1916, Lowell built an observatory in Arizona and dedicated much of his career to the study of Mars. He produced detailed maps showing an elaborate network of canals spreading across the planet's surface, which he interpreted as an irrigation system built by a dying Martian civilization, struggling to transport water from the polar ice caps to the drying equatorial regions. He wrote books. He gave lectures. He made Mars, for a generation of readers and thinkers, feel like a place where someone else had already tried and failed to survive. The canals were not real. Later, more powerful telescopes, and eventually spacecraft, showed that Schiaparelli's features and Lowell's elaborate network were artifacts of the limits of early telescopy, the eye-seeing patterns and the ambiguous blur at the edge of resolution. The mind, as it always does, had filled in the gaps with something meaningful. But the instinct behind the story was not entirely wrong either, because Mars had struggled with water, not in any way that required a civilization to manage it, but in the deep geological sense that the planet's surface bears the unmistakable marks of a world where water once flowed and then, over enormous spans of time, ceased to flow. Lowell was looking in the wrong place for the wrong kind of story. The real story of Mars and water was not written on the surface in straight lines. It was written in ancient valleys, in dried lake beds, in mineral deposits that swiftly form in liquid water, in geological formations so large they can only be seen from space. The real story was far older and far stranger than anything Lowell imagined. When the first spacecraft began flying past Mars in the 1960s, the early images were disappointing. Mariner 4, which flew past Mars in July 1965, returned 22 photographs showing a cratered, moon-like landscape. The surface looked dead and ancient. Scientists at the time concluded that Mars had probably always been cold and barren, a geologically inactive world that had never experienced anything like the conditions that make Earth alive. That conclusion did not last long. Mariner 9, which entered orbit around Mars in 1971 and became the first spacecraft to orbit another planet, revealed something that overturned everything the earlier flybys had suggested. Once a global dust storm that had been obscuring the surface cleared, the cameras began to show features no one had been prepared for. Enormous volcanoes. A
Yeah.
canyon system stretching nearly 4,000 kilometers across the surface, longer than the width of the continental United States, and critically ancient riverbeds. Channels that could only have been carved by flowing liquid, winding, branching, following gravitational contours the way rivers do on Earth. Something had once flowed on this planet, something liquid, something that carved valleys and left behind the signatures of a world that had been at some point in its long past very different from what it is now. That realization has only deepened in the decades since. Every mission to Mars, every orbiter, every lander, every rover, has added more detail to the picture of an ancient world that was wetter, warmer, and more complex than we initially believed. The question stopped being whether Mars had once had liquid water. The evidence for that became overwhelming. The question became, what happened to it? What kind of world was Mars before the water disappeared? And how long did that world last? Those are the questions that have quietly consumed planetary scientists for the past 50 years. They are also the questions we are going to sit with tonight. Because the story of what Mars was is not just a scientific puzzle, it is something stranger. It is the story of a world that seems to have had a chance, that had the ingredients, the conditions, the time, and then lost everything. So gradually that the loss itself is almost impossible to see in any single moment. Only across geological time, across hundreds of millions of years, does the full shape of what happened become clear. You have to stand very far back to see it, and when you do, what you see is not a catastrophe. What you see is a slow, quiet fading. There is a particular kind of knowledge that comes not from watching something happen, but from reading what it left behind. A forensic scientist walks into a room and reconstructs an event from the position of objects, the direction of marks on the floor, the chemical residue on a surface. A doctor reads an X-ray and sees inside a body without ever opening it. A geologist stands at the edge of a cliff face and looks at the layers of rock and reads time, not metaphorically, but literally. Each layer is a chapter. Each mineral, each fossil, each transition, from one rock type to another, is a sentence in a story that was written across millions of years and has been sitting there ever since, waiting to be read by someone who knows the language. Planetary scientists do something similar. They cannot travel back 4 billion years and watch Mars as it was. They cannot stand on the shores of an ancient Martian ocean and feel the wind or watch the water move. But they can read the surface. They can read the rocks. They can read the minerals, the topography, the crater patterns, the chemical signatures left behind by processes that ended long before any human being existed. And from that reading, they can reconstruct, carefully, imperfectly, but with growing confidence, what this planet was. The first tool is craters. Every solid body in the solar system accumulates craters over time, the result of impacts from asteroids, comets, and smaller debris left over from the solar system's formation. The longer a surface has been exposed, the older it is, the more craters it will have accumulated. This relationship between age and crater density gives planetary scientists a rough clock. A heavily cratered surface is an old surface. A relatively smooth surface is a younger one, resurfaced at some point by volcanic activity, erosion, ice, or liquid flow. When you look at a map of Mars, this variation is immediately visible. The southern hemisphere of Mars is heavily cratered, ancient terrain, some of it among the oldest surfaces in the solar system, dating back close to 4 billion years. The northern hemisphere, by contrast, is strikingly smooth, lower in elevation, with far fewer craters, suggesting that it was resurfaced at some point after the heavy bombardment of the early solar system had largely ended. That smooth, low-lying northern plain has a name, Vastatus Borealis, and one of the most significant ongoing debates in Mars science concerns what created it. Because the simplest explanation, the explanation that fits the topography, the geology, the elevation data, and the mineral signatures, is that much of the northern lowlands was once covered by a large body of standing water, an ocean or something very much like one. The idea of a Martian ocean is not new, and it remains debated. But the evidence that has accumulated in its favor over recent decades is substantial and comes from multiple independent directions. There is the elevation. Oceans on Earth occupy the lowest points of the surface. The Martian northern lowlands are the lowest region of the planet by a significant margin. If Mars once had enough liquid water to fill a large basin, this is exactly where it would have collected. There are the shoreline features. Several teams of researchers using high-resolution topographic data from orbiting spacecraft have identified long, sinuous features at consistent elevations that trace what could be the ancient coastlines of a northern ocean, places where a body of water met the land. These features are not perfectly continuous, and their interpretation is disputed, But their existence is difficult to explain without invoking standing water at some point in Mars's past. There is the mineralogy. Water does not simply sit on a surface and leave no trace. It reacts. It dissolves minerals, carries them, deposits them elsewhere, and leaves behind chemical signatures that persist for billions of years in the right conditions. Mars orbiters equipped with spectrometers have mapped the distribution of hydrated minerals across the surface. Minerals like phyllosilicates, which only form in the presence of liquid water, and sulfates, which form when water evaporates and leaves concentrated salts behind. The distribution of these minerals is not random. It follows the patterns you would expect from a world that once had large amounts of liquid water in specific locations at specific times. Then there are the valleys. The valley networks of Mars are among the most compelling pieces of evidence for an ancient wet climate. These are not subtle features. Some of them are enormous, branching systems of channels carved deep into the ancient southern highlands, stretching hundreds of kilometers with the unmistakable morphology of river drainage systems. They have tributaries. They follow gravity. They widen and deepen downstream in the way that rivers do when they carry increasing volumes of water. On Earth, drainage networks like these form over long periods of sustained rainfall and surface flow. The fact that Mars has them, carved into its oldest terrain, tells us that whatever process created them operated across geological timescales. This was not a brief event. This was not a single flood. This was a prolonged period, possibly hundreds of millions of years, during which liquid water moved persistently across the Martian surface. There is also Gale Crater, where NASA's Curiosity rover has been exploring since 2012. Gale Crater is approximately 150 kilometers wide. At its center sits a layered mountain, Mount Sharp, officially called Aeolus Mons, that rises about 5 kilometers above the crater floor. That mountain is made of sedimentary rock. Layer after layer of material deposited, compressed, and preserved over enormous spans of time. Curiosity has been slowly climbing through those layers, reading them the way a geologist reads a cliff face. And what the rover has found is one of the clearest records of ancient habitability anywhere on the planet. At the base of the mountain, in the oldest accessible layers, Curiosity found evidence of a lake. A long-lived lake, not a brief pool, but a body of water that persisted for possibly millions of years. The chemistry of the sediments indicates that the water was not extremely acidic or salty. It was, by the standards of what life requires, relatively benign. If you had been standing on the floor of Gale Crater perhaps 3.5 billion years ago, you might have been standing at the edge of a calm, shallow lake under a sky thick enough to hold weather. That thought deserves a moment. A calm lake on Mars, and Gale Crater is not unique. The Jezero crater, which is currently being explored by NASA's Perseverance rover, contains some of the clearest evidence of an ancient river delta on Mars. A fan-shaped deposit of sediment laid down where a river once slowed and spread as it entered a lake that filled the crater. Deltas are specific. They require sustained flow over sustained time. They require a source of water upstream and a body of standing water downstream. Jezero crater had both. The picture that emerges from all of this, from the valley networks, the crater lake sediments, the delta deposits, the mineral signatures, the topographic basin in the north, is of a planet that was genuinely, substantially wet during its early history. Not wet the way a damp sponge is wet, but wet the way a young, geologically active world is wet. With rainfall, perhaps. With rivers feeding lakes and seas. With a water cycle doing some version of what Earth's water cycle does. Evaporating, condensing, falling, flowing, collecting, evaporating again. How long did that wet period last? That is one of the harder questions, and the answer has shifted as new data has come in. Current estimates suggest that the most favorable conditions for liquid water on Mars existed roughly between 4 billion and 3 billion years ago, a window of perhaps 1 billion years, during the period planetary scientists call the Noachian and early Hesperian epochs. That is an enormous span of time. For context, complex animal life on Earth is only about 600 million years old. 1 billion years is longer than it took for multicellular life to appear on our planet after the conditions for life were established. But reading the surface only takes us so far. The valleys and lakes and deltas tell us that liquid water existed. They do not, by themselves, tell us how the planet maintained the conditions for liquid water. For that, we have to go deeper, not into the rock, but into the planet itself, into the atmosphere it once had, into the magnetic field that once protected it, into the geological engine that for a time kept everything running. Those are questions about forces. And to understand what Mars lost, we first have to understand what it once had. Science does not always move in straight lines. Sometimes a field builds slowly, adding one careful observation at a time, each new piece of data fitting neatly into the framework that already exists. and sometimes a single discovery or a cluster of discoveries arriving close together forces everyone to step back and reconsider assumptions they did not even know they were making. For Mars science, that kind of disruption has happened more than once. But perhaps no single shift in understanding was more significant than the one that came in the 1990s and early 2000s, when a new generation of spacecraft began returning data of a quality and resolution that earlier missions could not have produced. What those spacecraft found did not simply add detail to the existing picture of Mars. In several important cases, it changed the picture entirely. The instrument that perhaps did the most to transform our understanding was a spectrometer. Spectrometers measure light. More specifically, they measure the way different materials absorb and reflect light at different wavelengths. Every mineral has a characteristic spectral signature, a kind of fingerprint in light that allows scientists to identify what a surface is made of without ever touching it. When the Mars Global Surveyor and later the Mars Reconnaissance Orbiter began returning high-resolution spectral data from the entire Martian surface, planetary scientists found themselves looking at a mineral map of the planet that told a story nothing like the barren, always frozen world the earliest missions had suggested. They found phyllosilicates. Phyllosilicates are a family of minerals, clays, essentially, that form through a specific process, the prolonged interaction of rock with liquid water. Not a brief splash of water, not ice melting for a season and refreezing. The formation of phyllosilicates requires sustained contact between water and rock, often over timescales of thousands to millions of years, under conditions of moderate temperature and pressure. When you find phyllosilicates, you are not just finding evidence of water. You are finding evidence of a stable, long-lived, wet environment. The distribution of phyllosilicates on Mars was striking. They were concentrated in the oldest terrains, the heavily cratered southern highlands that date back to the Noachian period, more than 3.5 billion years ago. They were found in the walls of ancient craters, in the floors of old valleys, in regions where the ancient surface had been exposed by erosion or impact. They were widespread enough to suggest that the wet conditions that created them were not a local anomaly. They were a planetary feature. But the phyllosilicates were only the beginning. Alongside them, researchers found carbonates, minerals that form when carbon dioxide dissolves in water and reacts with calcium or magnesium in the rock. On Earth, carbonate rocks like limestone are enormously common and make up significant portions of the geological record. They form on the floors of shallow seas and lakes. Their presence in Mars's ancient terrain suggested not just water, but water with a chemistry complex enough to facilitate geochemical reactions between the atmosphere and the surface. The kind of chemistry that, on Earth, is deeply intertwined with the carbon cycle that helps regulate the planet's climate. They found sulfates, minerals like jarosite and gypsum that form when water containing dissolved sulfur compounds evaporates and the minerals precipitate out. The Mars Exploration Rover Opportunity, which landed in 2004 and operated for nearly 15 years, found thick deposits of sulfate-bearing rock in the ancient terrain of Meridiani Planum. The layers were extensive, finely bedded, and in some places showed the distinctive rippled patterns left behind by water moving across a shallow surface. These were not features that could be explained by wind alone or by ice or by any dry process. They required liquid water. Opportunity also found something smaller, but in its own way just as significant. Scattered across the surface at Meridiani Planum were tiny spherical objects, small enough to fit on a fingertip, roughly the size of a blueberry, that the science team nicknamed exactly that, blueberries. These were hematite concretions, spherical mineral formations that grow inside rock when iron-rich water moves slowly through porous material and deposits iron oxide in small, rounded masses around a central nucleus. On Earth, hematite concretions form in sedimentary environments that were once saturated with groundwater. Finding them at Meridiani Planum in enormous numbers, millions of them scattered across the surface like tiny ball bearings, was unambiguous evidence that liquid water had once moved through that rock. Each of these findings, taken alone, was significant. Together, they were overwhelming. By the mid-2000s, the scientific consensus had shifted decisively away from a Mars that had always been cold and dry, and toward a Mars that had experienced sustained liquid water across large areas of its surface for extended periods of its early history. But the finding that perhaps carried the most emotional weight, the one that made the ancient wet Mars feel most real, most tangible, was the discovery of the river deltas. We mentioned Jezero Crater earlier, but it is worth pausing here to understand what a delta actually represents, and why finding one on Mars mattered so much. A river delta forms at the mouth of a river, where the moving water slows as it enters a larger, calmer body of water. As the flow slows, it loses the energy needed to carry sediment, and that sediment falls out of suspension and settles on the floor. Over time, this process builds a fan-shaped deposit, wider downstream, narrower upstream, made up of sorted layers of material that record the history of the river's activity. The shape is distinctive. The internal layering is distinctive. And critically, a delta can only form if two things are simultaneously true. There must be a river carrying water and sediment from somewhere upstream, and there must be a body of standing water for the river to flow into. The delta in Jezero crater is clearly visible from orbit. It extends from the western rim of the crater in a classic fan shape, made up of layers of sediment that have been sitting there for somewhere between 3 and 4 billion years. The crater itself sits at an elevation consistent with having been a lake. There is an inlet channel on one side where water flowed in, and what appears to be an outlet channel on the other side where water flowed out when the lake reached a certain level. This is not an ambiguous feature. This is a lake system. A complete, coherent lake system, preserved on the surface of another planet, waiting to be read. Perseverance landed inside Jezero crater in February 2021, specifically because of that delta. The rover has been collecting rock samples from the ancient lakebed and delta deposits, samples that will eventually be returned to Earth by a future mission for detailed laboratory analysis. Scientists believe those rocks represent some of the best available opportunity to search for chemical or even physical traces of ancient life on Mars. But even before those samples reach a laboratory, the delta itself has told us something important. It tells us that the wet period on Mars was not simply a moment. It was not a brief, anomalous episode driven by a single volcanic eruption or a large impact that temporarily melted ice. The sedimentation recorded in the Jezero Delta required sustained, continuous flow over a long period. Estimates vary, but some researchers suggest the river system feeding the delta operated for at least 1 million years, and possibly much longer. 1 million years of flowing water on Mars. When you sit with that number, something shifts in how the planet feels. Mars does not feel like a dead place that was always dead. It feels like a place that was alive in some way, not biologically necessarily, but geologically, hydrologically, chemically alive for an enormous stretch of time. A place where complex things were happening, where water moved through rock and carried minerals and built deltas and filled craters and carved valleys, and somewhere in all of that, created conditions that may have been hospitable to the chemistry of life. And then, without any dramatic announcement, it stopped. The transition was not instantaneous. The evidence suggests it was gradual, a slow drying over hundreds of millions of years, a progressive retreat of surface water from most of the planet, a thinning of the atmosphere that made liquid water increasingly difficult to maintain. The phyllosilicates gave way to sulfates in the geological record, which suggests a shift from a relatively neutral, water-rich early Mars to a more acidic, drying Mars in the middle period. And then the sulfates gave way to the dry, oxidized dust of the modern surface. 3 chapters in mineralogy, 3 phases of a planet's life. The evidence that transformed Mars science was not a single discovery. It was this accumulation: valley networks, lake sediments, river deltas, clay minerals, sulfate deposits, hematite concretions, each one a thread in the same fabric, each one pointing in the same direction. Mars was wet. Mars was warm enough, for long enough, that water behaved on its surface the way water behaves on Earth. And then something failed. Understanding what failed and why requires us to look not at the surface, but at the forces that once held the whole system together. The atmosphere, the magnetic field, the heat inside the planet itself. Those forces were the difference between a living world and a desert. Close your eyes for a moment, if you like. Not to sleep, not yet, just to imagine. Try to picture a planet. Not the Mars of photographs, not the rust-colored desert that rovers have been slowly crossing for decades. A different Mars, an earlier one. A Mars from roughly 3.5 to 4 billion years ago, when the solar system was still young and turbulent, and the conditions on the inner planets were still being decided. This is difficult to do because we have no photographs of it. No one was there. The only record it left is written in minerals and rock formations and the shapes of valleys that have spent billions of years being slowly eroded by wind and radiation. Reconstructing what it looked like requires inference, careful, disciplined inference, built from multiple lines of evidence, and it requires holding a degree of uncertainty throughout. We are not describing something we saw. We are describing something we have reasoned toward. But the reasoning is solid enough that planetary scientists have been willing to commit to it, and the picture that emerges is remarkable. Begin with the sky. Mars today has an atmosphere so thin it exerts less than 1% of the pressure that Earth's atmosphere exerts at sea level. Standing on the Martian surface today, the air pressure would be roughly equivalent to what you would experience at an altitude of about 35 kilometers above Earth, far above the cruising altitude of any commercial aircraft, far above the altitude at which an unprotected human body could survive. The modern Martian atmosphere is, for most practical purposes, not there. But ancient Mars almost certainly had a much thicker atmosphere. We know this for several reasons. Liquid water cannot exist on the surface of a planet without sufficient atmospheric pressure. Below a critical threshold, water does not simply freeze. It sublimates directly from solid ice to vapor, skipping the liquid phase entirely. The fact that liquid water flowed on Mars for extended periods tells us, inescapably, that the atmosphere was once thick enough to prevent that sublimation. Estimates from climate models and geochemical data suggest that ancient Mars may have had an atmospheric pressure anywhere from several tenths to several times the current pressure on Earth. Enough to be substantial, enough to support weather. The composition of that ancient atmosphere was likely dominated by carbon dioxide, as it is today, but with important differences. There may have been significant amounts of water vapor. There may have been sulfur dioxide released by the enormous volcanic systems that were highly active in Mars's early history. There may have been other gases contributing to a greenhouse effect strong enough to keep surface temperatures above the freezing point of water, at least in some regions, at some times of year. The sky under that ancient atmosphere would have looked different from the pale pink-brown sky of modern Mars. Thicker air scatters light differently. Depending on the dust content and the specific composition of the atmosphere, the ancient Martian sky might have appeared more bluish at midday, not unlike Earth's sky, and would have supported clouds. Ice clouds almost certainly existed in the ancient Martian atmosphere, similar to the thin, wispy cirrus clouds that form in Earth's upper atmosphere. Some researchers have proposed that convective clouds, clouds associated with rising air currents and rainfall, may also have formed at least in specific regions or seasons. The possibility of rain on ancient Mars is one of the more vivid and difficult to absorb ideas in modern planetary science. Rain implies a complete water cycle. Rain requires water to evaporate from the surface, rise into the atmosphere, cool and condense into clouds, and fall back down. Rain requires an atmosphere substantial enough to carry moisture. Rain requires temperatures warm enough for liquid water to exist at the surface. Rain, sustained, repeated, geologically significant rain, is what carves the kinds of branching valley networks that Mars's southern highlands contain. Many researchers now believe that rainfall was the primary mechanism responsible for those valleys, rather than slow groundwater seeping to the surface, because the valley morphology matches the patterns that rainfall-driven erosion creates on Earth. If that is correct, and the evidence is increasingly favorable to it, then ancient Mars had weather, real weather, precipitation, storms perhaps. Seasons driven by the tilt of the planet's axis, which was different in the deep past and has changed considerably over time due to gravitational interactions with other planets. Now think about the surface under that sky. The topography of Mars, which we can measure with extraordinary precision from orbit, tells us where the water would have collected. The northern lowlands, the vast smooth basin of Vastas Borealis, sits several kilometers lower in elevation than the ancient southern highlands. If Mars had enough water, and the evidence suggests it did, that northern basin would have been an ocean. Not the entire northern hemisphere necessarily, but a substantial portion of it. A cold, shallow sea perhaps comparable in area to the Arctic Ocean or larger. The boundary between that hypothetical ocean and the ancient southern highlands would have been a coastline, a place where water met land. Some researchers have identified geological features at the margins of the northern lowlands that they interpret as ancient shorelines, long, sinuous ridges and scarps at roughly consistent elevations, the kind of features that form where waves and currents interact with land over long periods. These features are not universally accepted as shorelines, and the debate continues. But their existence is consistent with a northern ocean, and no better explanation for them has been proposed. South of that hypothetical coastline were the highlands, old, heavily cratered terrain, scarred by billions of years of impacts, but also crisscrossed by the valley networks that drainage from rainfall and snowmelt created. In this ancient landscape, water did not simply collect in the north, it moved. Rivers, some small and seasonal, some large and persistent, carried water from the higher terrain toward the lower, filling craters into lakes, building deltas where they slowed, carving canyons where the flow was concentrated. The largest canyon system in the solar system, Valles Marineris, stretches nearly 4,000 kilometers along the Martian equator and in places reaches depths of 7 kilometers. For comparison, the Grand Canyon is about 450 kilometers long and about 1.8 kilometers deep. Valles Marineris is roughly 10 times longer and 4 times deeper. It did not form the way a river canyon forms on Earth. It is primarily a tectonic feature, a vast system of rifts and faults in the Martian crust. But water played a role in its later history, widening and modifying its channels, filling portions of its floor with sediments. And then there were the volcanoes. Mars has the largest volcanoes in the solar system. Olympus Mons, the largest of them, is approximately 22 kilometers tall, nearly 3 times the height of Mount Everest above sea level, and covers an area roughly the size of France. The Tharsis Plateau, a vast elevated region that hosts Olympus Mons and several other enormous shield volcanoes, represents one of the most significant geological features in the entire solar system. In Mars's early history, this volcanic region was intensely active. That volcanic activity mattered enormously to what Mars was. Volcanoes release gases. They release water vapor, carbon dioxide, sulfur dioxide, and other compounds that, on Mars, were adding to the atmosphere rather than escaping from it. In the early Noachian period, Mars's volcanic outgassing may have been the primary mechanism that built and maintained the thick atmosphere that made liquid water possible. The volcanic heat also contributed to the hydrological system in other ways, heating groundwater, melting ice, driving hydrothermal activity that created warm, chemically rich environments in certain locations. Hydrothermal systems on Mars, places where volcanic heat met water, creating warm, chemically active environments that, on Earth, are some of the most productive habitats for microbial life. This ancient Mars, with its thicker sky, its possible ocean in the north, its rain-fed river systems in the south, its volcanoes building the atmosphere overhead and heating water below, was a genuinely complex planetary system. It was not Earth. It was colder than early Earth, on average, possibly with much of its water locked in ice that melted seasonally or during volcanically active periods. It had a weaker gravity. Mars is about a tenth of Earth's mass, which affected everything from atmospheric retention to how water moved across the surface. It had a different chemical composition, a different geological history, a different relationship to the sun. But it was not a desert, it was a world in progress. A world where geological and chemical processes were actively shaping the environment. A world with a water cycle, a carbon cycle, an atmosphere subject to weather. A world where, if you had arrived with the right instruments and the right questions, you would have found conditions that were, in at least some places and sometimes, not entirely unlike the early Earth. The question of life, of whether anything biological ever stirred in those ancient lakes and hydrothermal systems, we will return to later. For now, what matters is simply this world existed. This is not speculation about what Mars might have been given different circumstances. This is a description of what Mars actually was, based on evidence it has preserved in its rocks and minerals and topography across 4 billion years. The ancient wet Mars is not a hypothesis. It is the most well-supported interpretation of the available data. And it is gone, not overnight, not in a single catastrophe, but gone nonetheless. And to understand how something so substantial, a planetary water cycle, a thick atmosphere, a geologically active, hydrologically complex world, can disappear, we need to understand what was holding it together. Because what held it together was not permanent. It was never permanent. It was a set of conditions that existed for a time. And when those conditions changed, the world they had supported changed with them. In the next part of the story, we are going to look at those conditions. Starting with the one that may have mattered most, the one that Mars no longer has. You cannot see it. You cannot feel it. You cannot taste it or hear it or hold it in your hands. But it is there, surrounding the Earth right now, as it has surrounded the Earth for most of its history. A vast, invisible structure generated deep inside the planet, extending outward into space for tens of thousands of kilometers in every direction, shaping the paths of charged particles the way a river's banks shape the path of water. It has no color and no sound. It registers on no human sense. And without it, the world you are lying in right now would not be the world it is. It is called the magnetosphere, and it is one of the reasons you are alive. To understand why Mars became a desert, you have to understand what this invisible shield does. You have to understand what the solar wind is, and what happens to a planet that has nothing to deflect it. The sun is not a quiet object. It is a thermonuclear reactor, fusing hydrogen into helium at its core and releasing energy in quantities that are, by any human standard of measurement, almost impossible to express meaningfully. Some of that energy reaches us as light and heat, the radiation that warms the Earth's surface and drives the weather and makes photosynthesis possible. But the sun also releases something else, a constant, outward-flowing stream of charged particles, mostly protons and electrons, moving at speeds of hundreds to thousands of kilometers per second. This stream flows outward from the sun in all directions, continuously, reaching every planet in the solar system and extending far beyond the outermost planets into interstellar space. This is the solar wind. For a planet with a strong magnetic field, the solar wind is manageable. When the charged particles of the solar wind reach Earth, they encounter the magnetosphere, the region of space dominated by Earth's magnetic field. The magnetic field deflects those particles. Most of them are redirected around the planet, flowing past in curved paths that follow the magnetic field lines, never reaching the surface. The planet sits inside a protective bubble, relatively shielded from the full force of the particle stream flowing past it. The interaction is not invisible in all its consequences. At the poles, where the magnetic field lines converge and dip toward the surface, some particles do enter the upper atmosphere and collide with gas molecules there, exciting those molecules and causing them to emit light. This is what creates the aurora, the northern and southern lights. The aurora is, in a sense, the visible signature of the magnetosphere doing its job, deflecting the solar wind, channeling the particles that do get through toward the poles where they discharge harmlessly as light. Without the magnetosphere, those particles would not be deflected. They would strike the upper atmosphere directly, and that changes everything. Charged particles from the solar wind carry significant energy. When they strike atmospheric molecules, they transfer that energy, sometimes enough to knock electrons off the molecules entirely, ionizing them, and sometimes enough to give the molecules sufficient velocity to escape the planet's gravity altogether. This process, called atmospheric sputtering and ion escape, is not immediately catastrophic. It strips atmosphere slowly, molecule by molecule, over vast spans of time. But over hundreds of millions or billions of years, the losses accumulate. If nothing is replenishing the atmosphere, if the volcanic outgassing that once added gas has also slowed or stopped, the balance tips. The atmosphere thins. And as it thins, the rate of loss accelerates, because a thinner atmosphere is less able to protect itself. This is almost certainly what happened to Mars. Mars today has almost no global magnetic field. There are localized regions of magnetized crust, patches of ancient rock that retained their magnetization from a time when a global field existed. But there is no planet-wide magnetosphere surrounding Mars the way Earth's magnetosphere surrounds Earth. The solar wind strikes the Martian upper atmosphere essentially unimpeded, and the process of atmospheric loss is ongoing right now, measurable, being studied by NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, specifically to study how the planet's atmosphere interacts with the solar wind. MAVEN's measurements are striking. The spacecraft has detected streams of ions, primarily oxygen, carbon dioxide fragments, and other atmospheric constituents, being stripped from the Martian upper atmosphere and carried away by the solar wind. The current rate of loss is not enormous by geological standards. But MAVEN has also shown that the rate increases dramatically during solar storms, periods of intense solar activity when the solar wind becomes denser and more energetic than usual. During these events, the rate of atmospheric loss can increase by a factor of 10 or more. And the early sun was far more active than the sun today. Young stars are energetic stars. In the first billion years of the solar system's history, the sun was rotating faster and producing significantly more ultraviolet radiation and more powerful solar wind than it does today. The young Mars, losing its magnetic field during this period of heightened solar activity, would have been subjected to an atmospheric assault far more intense than anything MAVEN measures today. The losses during that early period were almost certainly much larger, much faster, much more consequential. But we are getting slightly ahead of ourselves. Before we can talk about Mars losing its magnetic field, we need to understand where that field came from in the first place. Earth's magnetic field is generated by a process called the geodynamo. The outer core of the Earth is made of molten iron and nickel, liquid metal, kept liquid by the enormous pressure and residual heat from the planet's formation. This liquid metal is in constant motion, driven by the heat escaping from the inner core and by the planet's rotation. As this electrically conducting liquid moves, it generates electrical currents, and those currents in turn generate a magnetic field. It is a self-sustaining process. The field induces currents in the moving liquid. The currents sustain the field, and as long as the liquid keeps moving, the field keeps being generated. The key requirement is motion in the liquid outer core, and that motion requires heat. The core must be hot enough, relative to the mantle above it, to keep the liquid metal churning. If the temperature difference between the core and the mantle decreases, if the core cools to the point where the heat flow is insufficient to drive vigorous convection, the motion slows. The electrical currents weaken. The magnetic field fades. Mars, it appears, lost its magnetic field because its core cooled. The evidence for this comes from those patches of magnetized ancient crust mentioned earlier. When you map them from orbit, which spacecraft like Mars Global Surveyor have done in detail, you find that they are concentrated in the oldest, most heavily cratered terrain of the southern highlands. The younger volcanic plains, including the enormous Tharsis region, show no significant magnetization. This pattern tells a story. Early in Mars's history, when those ancient crustal rocks were forming, a global magnetic field existed, and the rock recorded it as it cooled and solidified. But by the time the volcanic activity that built Tharsis was underway, perhaps 3.5 to 4 billion years ago, the global field had already weakened substantially or disappeared. The transition happened early. Geologically speaking, Mars lost its magnetic shield remarkably quickly, within the first few 100 million years of its history, possibly even faster. Why did the Martian core cool so much faster than Earth's? Size is the most important factor. Mars is a much smaller planet than Earth. It has roughly a tenth of Earth's mass and about half of Earth's radius. Smaller objects have a higher surface area to volume ratio than larger ones, meaning they lose heat to their surroundings more efficiently relative to the total heat they contain. A small stone pulled from a fire cools faster than a large boulder pulled from the same fire. The same principle applies to planets. Mars, being smaller, radiated away its internal heat faster than Earth did. Its core cooled faster, its geodynamo weakened, and then, relatively early in the planet's history, stopped. There may have been additional factors. The size and composition of the Martian core, the structure of the planet's interior, the thickness of its crust. All of these affect how heat moves through a planet and how long a geodynamo can be sustained. Mars may also have been struck by one or more large impacts in its early history that affected the structure of its interior in ways that accelerated core cooling. These details are still being worked out. But the fundamental story is clear. Mars had a magnetic field. That field protected the atmosphere from the solar wind. Then the core cooled, the geodynamo stopped, the field faded, and the planet was left exposed. What followed was slow, but it was irreversible. The solar wind, no longer deflected, began the long process of stripping the Martian atmosphere. The loss was not dramatic. There was no moment when the sky simply vanished. But over hundreds of millions of years, the balance shifted. The atmosphere that volcanic activity was adding from below was being taken away from above faster than it could be replaced. The pressure dropped, the greenhouse effect weakened, the temperatures fell. And as the temperatures fell, the conditions for liquid water became harder to maintain. The invisible shield had been holding everything together. When it failed, everything else followed. Imagine standing at the bottom of the ocean, not drowning, simply standing there, on the seafloor, with the entire weight of the water above you pressing down. The pressure you would feel is the weight of all that water stacked above your head, pulling toward the center of the Earth. It is crushing at great depths. Even at moderate depths, it is enough to collapse a human chest. Now imagine standing on the surface of the Earth on an ordinary day. You do not feel it. You have never felt it. But the weight of the atmosphere above your head, all the way up to the edge of space, the entire column of air pressing down on every square centimeter of your body, is approximately 10 newtons per square centimeter. That is about the same pressure as being 10 meters underwater. You carry that weight constantly from the moment of your birth, and you feel nothing. The body is built around it, shaped by it, made for it. The pressure is so familiar it has become invisible. That pressure is not incidental, it is essential. Without sufficient atmospheric pressure, liquid water cannot exist at the surface of a planet. Below a critical pressure threshold, about 0.6% of Earth's current atmospheric pressure, water has no stable liquid phase at all. It exists only as ice or vapor. Heat it up and it does not melt into liquid and then boil. It simply sublimates, passes directly from solid to gas, skipping the liquid state entirely. This is the condition Mars is in today. The atmospheric pressure at the Martian surface is about 0.6% of Earth's sea level pressure, right at that critical threshold, and in many places below it. This means that if you placed a cup of liquid water on the Martian surface today, it would not simply freeze. It would boil and freeze simultaneously, with the surface layer vaporizing into the near vacuum while the deeper layers crystallized into ice. The two processes would race each other. Within moments, the water would be gone, dispersed into vapor or locked into ice, depending on the temperature. Liquid water as a stable surface phenomenon simply cannot exist on Mars today, but it did exist. The evidence is undeniable. So the atmosphere at the time that water was flowing must have been very different. How different exactly is a question that planetary scientists have approached from multiple directions: climate modeling, geochemical analysis, crater morphology, mineral distribution, and the answers, while still carrying significant uncertainty, converge on a picture of an ancient Martian atmosphere that was substantially thicker than today's. The ancient atmosphere was almost certainly dominated by carbon dioxide, as today's is. But where the modern Martian atmosphere contains carbon dioxide at a pressure of roughly 600 pascals, the ancient atmosphere may have held carbon dioxide at pressures ranging from tens of thousands to perhaps even 100,000 pascals or more, potentially comparable to or exceeding Earth's current atmospheric pressure of about 100,000 pascals. Exactly how thick the ancient atmosphere was, and when it was thickest, remains debated. But the direction is not debated. It was substantially thicker than what exists today. Carbon dioxide is a greenhouse gas. When it is present in sufficient quantities in an atmosphere, it traps heat, absorbing outgoing infrared radiation from the surface and re-radiating it back downward, warming the surface above what it would be if the atmosphere were transparent to that radiation. This is the greenhouse effect, and it is not inherently dangerous or unusual. On Earth, the natural greenhouse effect from carbon dioxide, water vapor, and other gases raises the average surface temperature by about 33 degrees Celsius above what it would otherwise be. Without it, Earth's oceans would freeze. On ancient Mars, the greenhouse effect from a thick carbon dioxide atmosphere would have provided warming, but exactly how much and whether it was sufficient to keep water liquid on the surface is one of the most actively contested questions in Mars science. Here is the difficulty. Mars is farther from the Sun than Earth is. It receives less solar energy, about 43% as much as Earth receives per unit area. For liquid water to exist at the Martian surface, the greenhouse effect would have had to compensate for that reduced solar input and keep surface temperatures above 0 degrees Celsius, at least seasonally, at least in some regions. Climate models of the ancient Martian atmosphere have struggled to achieve this using carbon dioxide alone. Even with carbon dioxide pressures well above Earth's, many models produce an ancient Mars that is frozen on average, with liquid water only appearing during episodic warm periods driven by volcanic activity, large impacts, or orbital variations. Some researchers have proposed that additional greenhouse gases beyond carbon dioxide and water vapor may have played a role. Sulfur dioxide released in large quantities by volcanic eruptions is a potent greenhouse gas. Hydrogen gas, which can be produced by volcanic activity and by the interaction of water with iron-rich rocks, is also a greenhouse warmer when combined with carbon dioxide. Methane, which can be produced by geochemical reactions involving water and carbon dioxide in certain geological settings, is another possibility. Some combination of these gases, in the context of a thick carbon dioxide atmosphere, might have been sufficient to warm ancient Mars enough to maintain surface liquid water more persistently. The honest scientific position is that we do not yet fully understand how ancient Mars was warm enough. The evidence that it was warm enough, the valley networks, the lake sediments, the delta deposits, the hydrated minerals, is compelling. The mechanism that produced that warmth is still being worked out. This is not a failure of the science. It is one of the genuinely open questions at the frontier of planetary research. What is clear is that whatever the composition and structure of the ancient atmosphere, it was adequate. It did the job. For hundreds of millions of years, it maintained conditions at the Martian surface that allowed liquid water to persist in meaningful quantities. And then it stopped doing that job because it was being progressively stripped away. The stripping mechanism, the solar wind working on an unshielded atmosphere, has already been discussed. But there is another mechanism that also contributed to atmospheric loss, one that operates differently and on different timescales. Carbon dioxide can be removed from an atmosphere not just by being stripped into space, but by being chemically incorporated into rock. On Earth, this process is part of the long-term carbon cycle. Carbon dioxide dissolves in rainwater to form a weak acid, which weathers silicate rocks on the continents, and the resulting carbonate minerals are eventually carried by rivers to the ocean, where they are incorporated into seafloor sediments. Over geological time, this process draws carbon dioxide out of the atmosphere and sequesters it in rock. On Earth, volcanic activity eventually returns that carbon dioxide to the atmosphere, completing the cycle and keeping the atmospheric concentration of carbon dioxide roughly stable over long periods. On Mars, the first half of this cycle, carbon dioxide being drawn into rock, also operated. Carbonate minerals have been found in Martian rocks and soils. But the second half, the recycling of that carbon back into the atmosphere through volcanic activity, slowed as Mars's geological engine cooled. As the volcanoes became less active, less carbon dioxide was being returned to the atmosphere. As the atmosphere thinned, less carbon dioxide was available to be weathered into rock. The system, which on Earth is a self-regulating cycle, on Mars became a one-way street. Carbon gradually left the atmosphere and stayed in the rock. And then there is the water vapor. Water vapor is itself a greenhouse gas, a powerful one. In a warm, wet atmosphere, water vapor amplifies the warming effect of carbon dioxide, creating a positive feedback. More warmth means more evaporation, more water vapor in the atmosphere, more greenhouse warming. But this feedback works in reverse as well. As Mars cooled and the atmosphere thinned, water began freezing out of the atmosphere rather than evaporating into it. The water vapor concentration dropped. The greenhouse warming it had been providing weakened. The temperature dropped further. More water froze. The feedback accelerated the cooling. This kind of self-reinforcing process, where a small initial change triggers a cascade of further changes in the same direction, is called a runaway feedback. On Earth, climate scientists study the conditions under which runaway feedbacks might operate, because a similar but opposite runaway in the other direction, where warming causes more water vapor, which causes more warming, is one of the mechanisms that could, in extreme circumstances, turn a planet's climate from habitable to catastrophically hot. Venus may have experienced such a runaway greenhouse effect early in its history. Mars experienced the cold version, the slow, centuries-long collapse of its atmospheric warmth, driven by the interaction of atmospheric loss, volcanic decline, and self-reinforcing cooling feedbacks. By the end of the Noachian period, roughly 3.5 billion years ago, the Martian atmosphere had thinned substantially from its peak. Liquid water was becoming increasingly difficult to sustain. The rivers still flowed occasionally, perhaps fed by groundwater or by episodic volcanic heating or by impacts melting subsurface ice. But the age of persistent surface water was ending, and the sky, which had once been thick enough to hold clouds and weather, was becoming the thin, cold, nearly invisible thing it is today. The atmosphere did not disappear all at once. It drained away slowly, over billions of years, like air leaking from a sealed room through a crack too small to find but too persistent to ignore. And as it drained, everything that had depended on it drained away with it. There is heat inside the Earth right now. Not metaphorical heat, actual heat, thermal energy, moving slowly outward from the deep interior toward the surface, escaping into the atmosphere and then into space at a rate so gradual that on any human timescale it is essentially imperceptible. The ground beneath your feet is warmer than the air above it partly because of this. The slow, patient bleeding of heat from a planet that was born hot and has been cooling ever since. The Earth formed from the collision and accumulation of smaller bodies, planetesimals and protoplanets crashing together in the early solar system with enough energy that the entire young Earth was likely molten for a period. Those collisions converted kinetic energy into heat. The decay of radioactive isotopes in the Earth's interior, uranium, thorium, potassium, added more heat and continues to do so today. The Earth has been cooling from that original thermal budget for 4.5 billion years, and it still has not finished. The inner core is still hot, the mantle is still partially molten in places, the geodynamo is still running. Mars had the same beginning, the same collisions, the same radioactive decay, the same initial thermal budget. But Mars, being smaller, had a different relationship with that heat, and that difference shaped everything. To understand how warmth, specifically the warmth inside a planet, affects what happens on its surface, it helps to think about what geological activity actually does for a world. A geologically active planet is not simply a hot rock. It is a dynamic system in which heat drives movement of rock, movement of material from the interior to the surface, movement of gases from underground to the atmosphere. On Earth, this system expresses itself through plate tectonics, the slow, continuous movement of large slabs of the outer crust over the partially molten rock below. Plates collide, creating mountain ranges. They pull apart, opening rifts in ocean basins. They subduct, with one plate sliding beneath another, carrying surface material back into the mantle and returning volcanic gases to the atmosphere. Plate tectonics is, among other things, a recycling system. It recycles carbon, water, and other volatile compounds between the surface, the atmosphere, and the interior. It is part of what makes Earth's climate self-regulating over geological timescales. The long-term carbon cycle we mentioned in the previous chapter depends on the subduction of carbonate-bearing seafloor rock and the subsequent volcanic outgassing of that carbon back into the atmosphere. Mars, as far as we can determine, never had plate tectonics. Its crust appears to have been largely stationary, what planetary scientists call a stagnant lid system, in which the outer shell of the planet is a single, unbroken plate sitting on top of the interior. Without the churning, recycling mechanism of moving plates, material from the deep interior reached the surface primarily through volcanic hotspots, fixed points where rising plumes of hot mantle rock punch through the crust from below. On Earth, the Hawaiian Islands are the surface expression of such a hotspot, with the Pacific plate moving over it and creating a chain of volcanic islands. On Mars, where the crust did not move, The volcanic material simply piled up in the same location over and over again, building structures of extraordinary size. Olympus Mons is the result. 22 kilometers tall, 600 kilometers wide at its base, a shield volcano built by hundreds of millions of years of volcanic activity accumulating in one place, with no plate motion to spread the material around. But the significance of Mars's early volcanic activity goes beyond the size of its volcanoes. The significance is in what those volcanoes were releasing. In the early Noachian period, Mars's volcanic activity was intense. The planet was hotter, the mantle more vigorous, the eruptions more frequent and more voluminous than anything Mars has experienced in billions of years. Those eruptions were releasing gases, primarily water vapor, carbon dioxide, and sulfur dioxide, in enormous quantities. This volcanic outgassing was, in a real sense, building the ancient Martian atmosphere from below. Every eruption added mass to the atmosphere, adding pressure, adding greenhouse gases, contributing to the warmth that kept the surface above freezing. The geothermal heat associated with that volcanic activity also contributed directly to liquid water in another way. Beneath the surface, where rocks were heated by the cooling interior and by hydrothermal circulation, liquid water could exist even when surface temperatures were below freezing. Hydrothermal systems, networks of hot water moving through fractured rock heated by volcanic activity, would have been widespread in early Mars. These are not exotic environments. On Earth, hydrothermal systems exist wherever volcanic heat meets groundwater, and they host some of the most diverse and resilient microbial communities on the planet, including in the deep seafloor hydrothermal vents where sunlight never reaches, and where life depends entirely on the chemical energy released by the interaction of hot water with rock. The ancient Martian subsurface, heated from below and saturated with water from above, may have been an ideal environment for this kind of chemistry. Whether that chemistry ever crossed the threshold into biology is a question we will return to. But the physical conditions, heat, water, dissolved minerals, chemical gradients, were present. Now consider what happened as Mars's internal heat declined. The cooling of a planetary interior is not a sudden event. It happens gradually over hundreds of millions to billions of years as heat conducted through the mantle and crust is slowly lost to space. For Mars, that cooling process proceeded faster than on Earth, partly because of its smaller size and partly possibly because of its lack of plate tectonics. On Earth, plate tectonics acts as an efficient heat transport mechanism, bringing hot mantle material to the surface at mid-ocean ridges where it can cool rapidly. In a stagnant lid system like Mars, heat has to diffuse more slowly through the thick, stationary crust, which might seem like it would keep the interior hotter for longer. But the relationship between stagnant lid tectonics and heat loss is complex, and Mars's interior appears to have cooled faster than Earth's despite this. As the interior cooled, the volcanic activity slowed, eruptions became less frequent. The volumes of gas released declined. The contribution of volcanic outgassing to the atmospheric budget decreased and then eventually fell to near zero. The last significant volcanic activity on Mars is believed to have occurred perhaps a few 100 million years ago, possibly even more recently. Some researchers have suggested that certain volcanic regions on Mars may still be geologically active at a very low level, that Mars may not be entirely dead inside. But whatever activity remains is trivial compared to what the planet experienced in its early history. The decline of volcanic activity removed one of the key mechanisms that had been maintaining the ancient atmosphere. Without the continuous input of volcanic gases, the atmospheric losses to the solar wind and to chemical weathering were no longer being offset. The atmosphere began a long, slow decline. And as the internal heat declined, the hydrothermal systems that had been keeping water liquid underground also cooled. The warm, chemically active subsurface environments shrank. The groundwater retreated. The ice table, the depth at which underground water transitions from liquid to ice, descended. What had once been a complex, layered subsurface hydrological system simplified into permafrost and deep, cold brines. There is something worth pausing on here, in the middle of all this geology. The warmth inside a planet is not just a geological detail. It is one of the foundational requirements for a living world. Earth is alive in the geological and biological sense, partly because it is still warm inside. The same heat that drives plate tectonics and builds mountains and fuels volcanoes is also the heat that keeps the geodynamo running and the magnetic field in place. It is the heat that recycles carbon and water between the surface and the interior. It is the heat that powers the hydrothermal systems in the deep ocean, where some of the most fundamental chemistry of life may have first emerged. A planet's interior heat is not separate from its surface conditions. It is connected to them through dozens of interlocking processes, each dependent on the others. When Mars's interior cooled, it was not just losing heat, it was losing all of those processes simultaneously. The magnetic field, the volcanic outgassing, the hydrothermal systems, the carbon recycling, all of it tied together. All of it dependent, ultimately, on the heat that was slowly and irreversibly draining from the planet's core. And here is the thing that gives this story its particular quality of quiet inevitability. Mars could not have prevented this. There was no threshold it could have crossed to save itself. The cooling of its interior was a consequence of its size, a physical fact baked into the planet at the moment of its formation. A smaller planet loses heat faster. Mars was always going to cool faster than Earth. The only question was how long it would take, and what would survive in the time before it happened. The answer was a great deal. For perhaps 1 billion years, Mars maintained enough internal heat to support volcanic activity, enough atmospheric pressure to maintain liquid water, enough magnetic protection to prevent catastrophic atmospheric loss. 1 billion years is a long time. Whether it was long enough for something remarkable to happen in the lakes and hydrothermal systems of that ancient world, that is a question we will sit with carefully. But first, there is one more piece of the physical story to tell. Because the interior was not the only thing losing heat. Something else was also changing, something enormous overhead that was helping keep the ancient Martian surface warm. And understanding that requires us to look more carefully at the volcanoes. There is a mountain on Mars that should not be possible. By the standards of what we expect from planetary geology, by the physical constraints we understand from studying mountains on Earth, Olympus Mons should not exist. It is too tall, it is too wide. It has been building for too long, in one place, without interruption, piling volcanic material higher and wider over hundreds of millions of years, until it became something that no other rocky body in the solar system has produced. Standing at its base, you would not immediately know you were at the foot of a mountain. The slopes are so gradual, rising at an angle of only a few degrees, that the horizon would appear flat in most directions. The scale is simply too large for ordinary perspective to register. You would need to travel hundreds of kilometers outward before the ground began to slope away noticeably. And if you somehow stood at the summit and looked outward, you would see the curvature of the planet before you saw the base of the mountain disappearing below you. Olympus Mons is not just tall, it is wide enough to have its own horizon. It is, in geological terms, a shield volcano, the same broad, gently sloping shape produced by fluid basaltic lava flows that build outward as much as upward. Hawaii's Mauna Loa is a shield volcano. So is Iceland, in a sense, a broad, flat volcanic platform barely rising above sea level built by the same style of eruption. On Earth, shield volcanoes are large by terrestrial standards, but they are constrained by plate tectonics. As a tectonic plate moves over a volcanic hotspot, the volcano it builds is eventually carried away from the heat source, becomes dormant, and a new volcano begins forming behind it. The result is a chain of volcanic islands, rather than a single continuously growing mountain. On Mars, the plate did not move. The crust sat still over the Tharsis hotspot for billions of years, and the volcanic material just kept coming, eruption after eruption, century after century, building and building until something existed that has no counterpart anywhere else in the solar system. But tonight, Olympus Mons is not primarily interesting as a geological record breaker. It is interesting as a climate machine. To understand why, consider what a volcanic eruption actually releases. The dramatic imagery of eruptions, the rivers of lava, the pyroclastic flows, the ash clouds, tends to draw attention to the solid and liquid material being expelled. But volcanoes are also, and perhaps more importantly from a planetary climate perspective, gas-releasing events. Every eruption expels large quantities of volatile compounds that have been dissolved in the magma under pressure and are suddenly free to escape when that magma reaches the surface. On Earth, volcanic gases are primarily water vapor, carbon dioxide, and sulfur dioxide, with smaller amounts of other compounds. On Mars, the composition was broadly similar, and in the early Noachian period, when the Tharsis volcanic province was in its most intense phase of activity, the quantities of gas being released were staggering. Estimates of the total volume of gas outgassed by the Tharsis volcanoes over their full history vary, but some calculations suggest that the water vapor alone may have been sufficient, if it had all rained out onto the surface, to cover the entire planet in a global ocean tens of meters deep. The carbon dioxide released may have been sufficient to create an atmospheric pressure several times higher than Earth's current atmospheric pressure. These are rough estimates with large uncertainties. The history of Tharsis volcanism is difficult to reconstruct in detail, but they give a sense of the scale of what was happening. The ancient Martian sky was in a very real sense built by volcanoes. The carbon dioxide thickened the atmosphere and enhanced the greenhouse effect. The water vapor added further greenhouse warming and eventually rained out, filling the valleys and lakes and possibly the northern ocean basin. The sulfur dioxide, though it eventually reacted with water to form sulfuric acid aerosols and sulfate minerals, may have provided additional short-term warming during intense eruptive periods. The whole system was being fed from below, with the volcanic interior of the planet continuously restocking the atmospheric reservoir that solar wind and chemical weathering were continuously depleting. For a time, the balance held. The period of peak Tharsis volcanism coincides roughly with the period of peak Martian habitability, the Noachian epoch, from roughly 4 billion to 3.5 billion years ago. This is not a coincidence. The volcanism was a primary driver of the conditions that made that period hospitable. Without the continuous outgassing of the seistarous volcanoes, the atmosphere would have thinned faster, the greenhouse effect would have weakened sooner, and the window of liquid water at the surface might have been much narrower. But the volcanic activity was not uniform over time. Even within the Noachian period, there were almost certainly periods of intense activity interspersed with quieter intervals. And researchers have proposed that some of the features of ancient Mars, including episodic flooding events that carved enormous outflow channels, may have been driven by sudden, catastrophic releases of volcanic heat and gas that temporarily melted large amounts of subsurface ice and sent floods of water rushing across the surface. These outflow channels are among the most dramatic features on Mars. They are not the same as the valley networks carved by rainfall and slow erosion. They are wide, deep, sudden channels that in some cases are hundreds of kilometers wide and clearly formed by catastrophic floods rather than gradual river flow. The volume of water implied by some of these channels is extraordinary. In some cases, individual flood events may have released volumes of water comparable to the combined flow of the largest rivers on Earth, all at once, carving kilometers of rock in a geological instant. What could cause such sudden massive releases of water? The most favored explanation involves volcanism interacting with permafrost. If a volcanic intrusion, a body of hot magma pushing up through the crust without necessarily reaching the surface, were to encounter a large reservoir of ground ice or liquid water, the result could be rapid melting and vaporization of that water, building up pressure until it burst catastrophically through the overlying rock. Something like a geological pressure cooker suddenly losing its lid. This kind of event would release not just water but also large amounts of volcanic gas, carbon dioxide, water vapor, sulfur dioxide, potentially causing short-term spikes in atmospheric pressure and temperature. Mars's climate history may have been punctuated by these episodic warm-wet intervals driven by volcanic events, separated by longer cold and dry periods when the baseline climate was closer to what we see today. If that picture is correct, then ancient Mars was not uniformly warm and wet. It was episodically warm and wet, a planet that oscillated between frozen, quiet, and volcanic-driven warmth, with liquid water available at the surface during the warm intervals and locked in ice during the cold ones. This has important implications for the question of life, which we will return to later. But for now, what matters is the trajectory. The volcanic activity that drove these warm intervals, that built the atmosphere, that melted the ice, that fed the lakes and the rivers, was itself powered by the heat inside the planet. And that heat was declining. Each successive period of volcanic activity was somewhat less intense than the last. The eruptions became less frequent. The volumes of gas released became smaller. The warm intervals became shorter and farther apart. And gradually, the baseline climate shifted permanently toward the cold and dry. The last major volcanic activity in the Tharsis region may have occurred within the last few 100 million years, geologically recent but a shadow of what had come before. By that point, the atmosphere had already thinned to a fraction of its ancient thickness. The surface water was already long gone. The volcanic activity that remained was a quiet echo of what had once fed the sky. There is something in this that feels almost biological, the way a living system depletes its resources over time, the way energy flows diminish as the gradients that drive them are slowly consumed. Mars was never alive in that sense, but the interplay between its volcanic interior and its atmospheric and hydrological systems had a quality of interconnection, of mutual dependence, that resembles the kind of system we associate with living things. Everything was connected. The heat inside fed the volcanoes fed the atmosphere. The atmosphere kept the water liquid. The liquid water shaped the surface and created the conditions for chemistry. And then, from the bottom up, the connections began to fail. The heat declined. The volcanoes quieted. The atmosphere thinned. The water retreated. And the planet that had been, for 1 billion years, something genuinely complex and dynamic, slowly became the still, cold, rust-colored desert that a small robotic vehicle is crossing right now, taking photographs and collecting rocks for a humanity that will not receive them for years. There is a moment in the life of a fire when it stops being a fire. Not when the last flame goes out. That is already the end of something that began earlier in a quieter way. The real ending happens before that. It happens when the fire stops generating enough heat to sustain itself. When the balance tips from combustion feeding combustion to heat loss, outpacing heat generation. The flame may still be visible for some time after that moment. It may still feel warm if you hold your hand near it. But the process that was keeping it alive has already ended. What remains is only the slow expiration of what was stored. Something like this happened inside Mars. Not quickly, not dramatically. Over hundreds of millions of years, the deep interior of the planet crossed a threshold from which there was no return. A threshold where the heat still present was no longer sufficient to maintain the churning, convective motion in the liquid outer core that had been generating the planet's magnetic field. The fire, in this sense, was still burning, but it had weakened past the point where it could sustain the process that mattered most. And when the core went quiet, Mars began to die. To understand what happened, we need to go deeper into the planet than any spacecraft has ever reached. We need to think about the structure of a rocky planet's interior, about what is down there, how it behaves, and why its behavior matters so enormously to everything happening thousands of kilometers above it at the surface. A rocky planet like Mars or Earth is not uniform throughout. It is layered, like an onion, with each layer having different properties determined by the composition of the material and the temperature and pressure at that depth. At the very center is the core, the densest material, primarily iron and nickel, which sank toward the center when the planet was young and molten, pulled there by gravity in a process called differentiation. Above the core is the mantle, a thick layer of silicate rock that, despite being solid in the conventional sense, behaves over geological timescales like an extremely viscous fluid, capable of flowing very slowly in response to temperature differences. Above the mantle is the crust, the thin, rigid outer shell that we walk on, drill into, and read the history of the planet from. The core of a rocky planet can exist in two states. If it is hot enough, part or all of it is liquid, molten iron and nickel, able to flow. If it has cooled sufficiently, it solidifies. On Earth, the inner core is solid iron, surrounded by a liquid outer core of iron and nickel. It is the motion of that liquid outer core, driven by heat flowing outward from the inner core and by the planet's rotation, that generates Earth's magnetic field. The key word is motion. The geodynamo requires the liquid metal to be in motion, and motion requires a temperature difference. Heat flowing from the hotter inner regions toward the cooler outer ones, driving convection the way heat drives convection in a pot of water being heated from below. Hot water rises, cool water sinks, and the circulation continues as long as the heating continues. For Mars, the question of what happened to its core is one that scientists have been working to answer for decades. Until recently, direct evidence was limited. We could infer the likely structure of the Martian interior from the planet's mass, its moment of inertia, and the behavior of its magnetic field, but we could not measure it directly. That changed with NASA's InSight lander. InSight arrived on Mars in November 2018 and carried, among other instruments, a seismometer, a device designed to detect Marsquakes, the Martian equivalent of earthquakes, and to use the seismic waves generated by those quakes to probe the interior of the planet the way a doctor uses ultrasound to see inside a body. Seismic waves travel at different speeds through different materials, and they bend and reflect at boundaries between layers of different density and composition. By recording these waves and analyzing their behavior, seismologists can infer the size, composition, and physical state of a planet's interior layers. InSight's seismic data, published in a series of papers in 2021 and 2022, gave us the first direct measurements of the Martian interior. The results were surprising in some ways and confirmatory in others. The Martian core, InSight found, is larger than some models had predicted. With a radius of approximately 1,800 kilometers, about half the total radius of the planet. It is liquid, molten iron, confirming that Mars is not yet completely solidified at its center. And it appears to be less dense than a pure iron-nickel core would be, suggesting the presence of lighter elements, sulfur, oxygen, hydrogen, or carbon, mixed into the iron. The presence of lighter elements in the Martian core is significant. Light elements lower the melting point of the iron mixture, which means the core remains liquid at lower temperatures than a pure iron core would. This sounds like it should help sustain a geodynamo. A liquid core can generate a magnetic field. But the same light elements also affect the way heat flows through the core, potentially suppressing the kind of vigorous convection needed to drive a strong magnetic field. The current Martian core is liquid, but it is not generating a global magnetic field. This tells us something important. Having a liquid core is necessary but not sufficient for a geodynamo. You also need the right kind of heat flow. Enough of a temperature difference between the inner and outer parts of the core to drive convection at the scale needed to generate a significant magnetic field. Mars appears to have lost that heat flow very early in its history. The ancient magnetized crust in the southern highlands, those patches of rock that recorded a global magnetic field when they cooled more than 4 billion years ago, tells us that a field existed then. The absence of magnetization in younger volcanic rocks tells us the field had already weakened or disappeared by the time those rocks formed, perhaps 3.5 to 4 billion years ago. Why did the heat flow in the Martian core decline so rapidly? Several factors likely contributed. The relatively small size of the planet meant less total heat to begin with and faster overall cooling. The possible presence of light elements in the core may have suppressed convection. The lack of plate tectonics, which on Earth helps draw heat out of the mantle efficiently and maintain the temperature gradient that drives core convection, may have paradoxically allowed the lower mantle of Mars to warm up over time, reducing the temperature difference between the core and the mantle above it and weakening the convective driving force. There is also the question of whether Mars may have experienced a giant impact early in its history, a collision with a large body that disrupted the structure of the planet's interior and affected how heat was distributed within it. The dichotomy between the ancient, heavily cratered southern highlands and the smooth northern lowlands, the most dramatic topographic feature on Mars, has been attributed by some researchers to exactly such an impact. If a body roughly the size of the Moon struck the young Mars at low velocity, it could have excavated the northern lowlands and deposited material in a thick layer in the south, creating the dichotomy we see today. Such an impact would also have profoundly affected the thermal structure of the planet's interior, potentially contributing to the early shutdown of the geodynamo. This remains one of the unsettled questions in Martian geology. The origin of the crustal dichotomy, whether impact or internal dynamics or some combination, is still debated. But whatever the cause, the outcome is clear. The magnetic field faded, and it faded early. And with the fading of the magnetic field, the protection it had provided to the atmosphere began to disappear. There is a particular kind of quiet that comes after something large and fundamental stops. Not silence exactly. The world continues, other processes continue. The surface of Mars continued to be shaped by wind and impact and the slow chemistry of dust interacting with thin air. But something essential was gone. The deep engine that had been powering the magnetic shield, enabling the atmosphere to persist, allowing the water to flow, that engine had slowed past the point of useful function. The planet was still there. It would be there for billions of years more. It is still there now, still orbiting the sun on its schedule, still showing that rust-colored face to anyone who knows where to look in the night sky. But the process that had briefly, on cosmic timescales, made it something more than a rock had ended. What followed was not an event, it was an absence. A long, slow absence of the things that had made Mars, for a time, genuinely interesting. The solar wind, no longer deflected, began its patient work on the unprotected atmosphere. The volcanic activity, no longer driven by vigorous internal convection, began to slow. The hydrothermal systems, deprived of their heat source, began to cool. The water, deprived of the atmospheric pressure that kept it liquid, began to freeze and evaporate. Mars was entering a new phase of its existence. Not death exactly. A planet does not die the way a living thing dies. There is no moment of cessation, no last breath. There is only the slow transition from one state to another, from dynamic to static, from complex to simple, from wet to dry, from warm to cold. That transition was already underway. Step outside on a clear night and look up. The sun is gone, below the horizon on the other side of the planet. But it is not inactive. It is never inactive. Right now, in this moment, while you lie still and the world around you is quiet, the sun is releasing a stream of charged particles in every direction, outward, away from itself, flowing through the solar system at speeds ranging from 400 to 800 kilometers per second, through the space between the planets. Past Mercury, past Venus, past Earth, past Mars, continuing outward past Jupiter and Saturn and the distant ice giants, all the way to the edge of the heliosphere where the solar wind finally meets the interstellar medium and slows to a stop. This stream has been flowing continuously for 4.5 billion years. It has never stopped. Not for a day, not for an hour. Through every geological epoch on Earth, through every ice age and warm period, through the entire history of life from the first single-celled organisms to the moment you are reading this, the solar wind has been flowing. It is one of the most constant features of our solar system, a permanent condition of the space between the planets, as continuous and as ancient as the sun itself. On Earth, you do not feel it. The magnetosphere deflects it. The atmosphere absorbs the small fraction that gets through. Your body has never been touched by the solar wind, not directly, because the planet you live on has spent billions of years building and maintaining the systems that stand between you and it. The solar wind is, to most humans, an abstraction, something that exists in textbooks and in the beautiful light of auroras, but not something that registers as a presence. On Mars, there is no such protection, not anymore. And to understand what that means, what it actually means physically, for a planet to be exposed to the solar wind over billions of years, we need to understand what the solar wind actually is, and what it does when it meets an atmosphere with nothing to stop it. The solar wind is not wind in the sense we usually mean. It is not a movement of gas the way Earth's wind is a movement of air molecules. It is a plasma, a state of matter in which atoms have been stripped of their electrons, leaving a mixture of free electrons and positively charged ions flowing together. The primary components are protons and hydrogen nuclei, and electrons, with smaller amounts of helium nuclei and trace quantities of heavier ions. This plasma is ejected continuously from the sun's upper atmosphere, the corona, where temperatures reach millions of degrees Celsius, and the thermal energy of the gas is sufficient to overcome the sun's gravity and allow the plasma to escape into space. The solar wind carries energy, not enormous amounts by the standards of, say, a volcanic eruption or a large impact, but enough, delivered continuously over billions of years, to do significant work on whatever it encounters. When the solar wind reaches a planet, several things can happen, depending on what that planet has to defend itself. A planet with a strong magnetic field like Earth deflects most of the solar wind before it reaches the atmosphere. The charged particles are redirected by the magnetic field lines, flowing around the planet in a teardrop-shaped cavity called the magnetosphere. The atmosphere is largely protected. The interaction is visible at the poles as aurora, but the damage to the atmosphere is minimal. A planet with no magnetic field but a thick atmosphere like Venus presents a different situation. The solar wind interacts directly with the upper atmosphere, the ionosphere, where solar radiation has ionized the upper atmospheric gases. The ionosphere creates its own weak induced magnetic field from the interaction with the solar wind, which provides some protection. Venus is losing atmosphere to the solar wind, but relatively slowly, partly because of its thick atmosphere and partly because of its proximity to the sun, which creates a stronger solar wind pressure that paradoxically compresses the interaction region and limits the volume of atmosphere exposed. Mars has neither of these defenses in any significant form. Its magnetic field is essentially absent. Its atmosphere is too thin to create a robust induced magnetosphere. The solar wind strikes the upper Martian atmosphere almost directly, and the results have been measured in detail by the MAVEN spacecraft. MAVEN, the Mars Atmosphere and Volatile Evolution mission, arrived at Mars in September 2014 with a specific mandate: to study how Mars is currently losing its atmosphere to space, and to use that information to understand how the ancient atmosphere was lost over time. It was, in a sense, a forensic investigation. The crime had already happened billions of years ago. MAVEN was gathering evidence from the scene. What MAVEN found was a portrait of a planet being slowly, continuously disassembled. The spacecraft measured ions, charged atmospheric particles, streaming away from Mars in the direction of the solar wind's flow, carried off into space by the interaction between the solar wind and the upper atmosphere. The most abundant ion being lost is oxygen, specifically, oxygen that has been stripped from carbon dioxide molecules in the upper atmosphere by solar ultraviolet radiation, ionized, and then picked up by the solar wind's electric and magnetic fields and accelerated away from the planet. The current rate of loss is modest, on the order of 100 grams of atmosphere per second. That sounds small, and in absolute terms it is. But MAVEN also showed that during solar storms, coronal mass ejections, in which the sun releases enormous bursts of plasma and magnetic field, the rate of atmospheric loss increases dramatically. During a major solar event observed by MAVEN in March 2015, the rate of ion escape increased by a factor of 10 to 20 compared to baseline conditions. And the early sun, as mentioned previously, was far more active than the sun today. It rotated faster. It produced more ultraviolet radiation. It generated more frequent and more powerful solar storms. The early solar wind was denser and more energetic. The young Mars, having just lost its magnetic field, was subjected to this more intense early solar wind with no protection whatsoever. Extrapolating from current measurements back through time, accounting for the higher activity of the early sun, the total atmospheric mass lost from Mars over the past 4 billion years is estimated to be substantial, possibly comparable to or exceeding the mass of the current Martian atmosphere many times over. The ancient atmosphere, which was thick enough to support liquid water, has been largely stripped away, molecule by molecule, ion by ion, over billions of years of continuous solar wind erosion. The process has a name. Scientists call it ion escape or atmospheric sputtering or more generally atmospheric loss to space. The terminology is clinical and precise, but the reality it describes is something more evocative. A planet being slowly eaten, from the top down, by the relentless outflow of its parent star. There is something worth sitting with in the relationship between Mars and the Sun. The Sun gave Mars the energy it needed to maintain liquid water at its surface during its early history. Solar radiation warmed the ground. Solar energy drove the early Martian water cycle, evaporating water into the atmosphere and cycling it back as rain or snow. In this sense, the Sun was a source of the conditions that made ancient Mars what it was. But the Sun also took those conditions away. The same Sun that warmed the ancient Martian surface was also through its solar wind, slowly stripping the atmosphere that made that warming possible. It was a relationship with two opposing forces, the electromagnetic radiation that warmed and sustained, and the particle radiation that eroded and destroyed. While the magnetic field was in place, Mars was protected enough that the sustaining force won. When the magnetic field failed, the eroding force began to gain the upper hand. The balance tipped. Gradually, over millions of years, the atmospheric losses began to exceed the volcanic inputs that were trying to offset them. The pressure dropped, the greenhouse effect weakened, the surface cooled, the water retreated. What Maven is measuring today is the tail end of a process that began billions of years ago. The dramatic part, the part where the ancient, thick atmosphere was stripped away, happened long before any spacecraft was there to witness it. What remains is the slow, continuing erosion of what little is left. A thin, cold atmosphere being gently, persistently reduced by a solar wind that has never, in 4.5 billion years, taken a single day off. Every second right now, Mars is losing approximately 100 grams of its atmosphere to space. It is a small number, almost nothing by planetary standards. But it has been happening every second for 4 billion years. And the cumulative result of all those seconds, all that quiet, continuous loss, is the near vacuum that exists above the Martian surface today. The ghost of an atmosphere, the remnant of something that was once substantial enough to hold weather, to keep water liquid, to make a world possible. It is gone because nothing was there to stop what was always flowing. There is a way of reading loss that does not require witnessing the moment something disappears. A tree falls in a forest and rots over decades, and eventually what remains is a long depression in the soil, a ghost outline of something that was once solid and tall, readable to anyone who knows what a depression in that particular shape means. A river dries up over centuries, and the channel it carved remains, curving through the landscape, telling anyone who comes later exactly where the water was and roughly how much of it there was and in what direction it was moving. The evidence of absence, if you know how to read it, can be as informative as the thing itself. Mars has left exactly this kind of record. The disappearance of its atmosphere was not witnessed by anyone. There were no instruments recording the pressure readings as they declined. There was no moment of measurement when scientists noted that the thick ancient air had become the thin modern remnant. The loss happened across geological time, written not in data logs but in minerals and landforms and isotopic ratios, a kind of record that can be read billions of years later by spacecraft and rovers that were not yet imagined when the loss was occurring. Reading that record is one of the central achievements of modern Mars science, and what it tells us is a story of loss so gradual and so complete that it feels, in retrospect, almost inevitable. Begin with the isotopes. Isotopes are variants of the same chemical element that differ in the number of neutrons in their nuclei. Carbon-12 and carbon-14 are both carbon, but they have different masses. Most elements exist as mixtures of isotopes, and the ratio of those isotopes in a given sample can tell scientists an enormous amount about the history of that material. For Mars's atmosphere, the most informative isotopic signature comes from comparing the ratio of lighter to heavier isotopes of certain elements, particularly argon, xenon, nitrogen, and carbon, between the current Martian atmosphere and what we would expect the original Martian atmosphere to have had based on solar system formation models. The key insight is simple. When an atmosphere is being stripped away, when particles are escaping to space, the lighter isotopes escape more easily than the heavier ones. A lighter particle, moving at the same temperature, moves faster. It is more likely to reach escape velocity. It is more likely to be picked up by the solar wind. Over time, as the atmosphere loses preferentially more of its lighter isotopes, the ratio of heavy to light isotopes in the remaining atmosphere increases. The atmosphere becomes progressively enriched in the heavier variants. This is exactly what we find in the current Martian atmosphere. The ratio of heavy to light isotopes in the Martian atmosphere is significantly elevated compared to what would be expected from a primordial, unprocessed atmosphere. In some elements, the enrichment is dramatic. The ratio of heavy nitrogen to light nitrogen in the Martian atmosphere, for example, is about 1.7 times the ratio found in Earth's atmosphere or in Martian meteorites, which preserve a record of the ancient Martian atmosphere when they were first formed. The ratio of heavy noble gas isotopes tells a similar story. These ratios aren't just qualitative evidence that the atmosphere has been lost. They are quantitative constraints. By modeling the isotopic fractionation that would result from different amounts of atmospheric loss, scientists can estimate how much atmosphere Mars has lost over its history. The numbers are large. The current thin Martian atmosphere appears to be a small residual fraction of what once existed, perhaps a few percent of the original atmospheric mass, possibly less, with the rest having escaped to space or been sequestered into the rock. The rock sequestration is itself a significant part of the story. We discussed in an earlier chapter how carbon dioxide can be drawn out of an atmosphere and incorporated into carbonate minerals through chemical weathering. On Mars, this process operated throughout the planet's history, though perhaps not as efficiently as on Earth, partly because Mars lacked the plate tectonic recycling mechanism that returns carbon from rock to atmosphere. The result is that some fraction of the ancient Martian atmosphere is not in space. It is in the ground. Carbonate minerals have been detected in Martian rocks by orbiters and rovers, though in smaller quantities than some early models predicted. The distribution and abundance of carbonates on Mars is itself a subject of active research, with implications for understanding both the ancient climate and the current atmospheric budget. Recent work has suggested that significant carbonate deposits may be buried beneath the Martian surface, hidden from orbital observation, which could mean that more of the ancient atmosphere is sequestered in rock than the surface detections alone would suggest. There is also the polar ice caps. Mars has 2 polar ice caps, one at each pole, made of layers of water ice and frozen carbon dioxide, dry ice. These caps are not just geological features, they are atmospheric reservoirs. The carbon dioxide that condenses at the poles in winter and sublimates back into the atmosphere in spring is part of a seasonal exchange that currently constitutes the dominant component of the Martian atmospheric cycle. In winter, up to a third of the entire Martian atmosphere freezes out onto the polar caps. In spring, it returns. This seasonal breathing of the atmosphere is one of the most striking aspects of modern Mars, a planet so cold that its own air periodically freezes solid. But it also hints at a possible route to a slightly thicker atmosphere, if the polar caps were somehow warmed, by a change in Mars's orbital parameters, by a large impact, by some future human engineering effort. The frozen carbon dioxide would sublimate into the atmosphere, adding to the atmospheric pressure. How much carbon dioxide is locked in the polar caps? Estimates have varied, but the most recent detailed measurements suggest that the South Polar Cap alone contains enough frozen carbon dioxide to roughly double the current atmospheric pressure if it were all sublimated. That would still leave Mars with an atmosphere far thinner than what is needed for liquid water at the surface, but it illustrates that the modern thin atmosphere is not the full picture of where Mars's atmospheric budget has ended up. Some is in space, stripped away by billions of years of solar wind erosion. Some is in the rock, chemically weathered into carbonate minerals. Some is at the poles, frozen solid each winter and partially returned each spring. And some remains in the thin, cold, nearly transparent atmosphere that surrounds the planet today. Barely there, barely measurable by human standards, but still present. Still doing the small amount of work that a 600 Pascal atmosphere can do, creating the faintest weather, carrying dust in global storms, participating in the seasonal exchange with the polar caps. Now consider the timescale of all this. The transition from the ancient thick atmosphere to the modern thin one was not instantaneous. The evidence suggests it was a multi-stage process, spread across more than 3 billion years. The most dramatic losses probably occurred during the Noachian and early Hesperian periods, the first 1 to 1.5 billion years of Mars's history, when the young, active sun was bombarding the newly unprotected atmosphere with its more intense early solar wind. During this period, the losses may have been rapid enough to be considered geological events in their own right. But the losses continued more slowly through the Hesperian and into the Amazonian, the current epoch, which began roughly 3 billion years ago and continues to the present day. The thin atmosphere we measure today is the result of both the early catastrophic losses and the continuing slow erosion of what survived. What strikes a person sitting with this history is not the drama of it. There is no drama. There was no explosion, no impact, no moment of catastrophe that ended the ancient Martian atmosphere. There was only the patient, continuous work of solar wind erosion and chemical weathering, operating on a planet that had lost the defenses that might have slowed them. Billions of years of unspectacular, relentless loss, and the planet did not resist it. It could not. Resistance would have required the things Mars had already lost: the magnetic field, the vigorous volcanism, the thermal engine that might have sustained both. Without those, the outcome was determined. Not immediately, not quickly by any human standard, but determined. There is something philosophically interesting in the idea of a determined outcome that takes billions of years to arrive. From inside that process, if there had been anything inside it to observe, each individual moment would have seemed unremarkable. The atmosphere on any given day of the Hesperian period would have seemed essentially identical to the atmosphere the day before. The change was too slow for any individual snapshot to capture. Only across the full arc of geological time does the magnitude of the transformation become visible. This is how most of the large changes in the universe work. Not in moments, but in the accumulation of moments. Not in events, but in the direction of processes too slow to watch. The Martian atmosphere was stripped away in exactly this manner, without witnesses, without a single definitive moment. Across a span of time so large that the entirety of human history, every civilization, every war, every invention, every generation of human beings who has ever lived, would occupy less than 1,000% of it. And when the stripping was complete, or nearly so, what remained was a world from which liquid water could no longer exist. The water had its own story to tell, its own way of disappearing. Water is patient in a way that most things are not. It waits in rock, locked in the crystal structure of minerals, for billions of years. It moves through soil and stone at rates too slow to observe directly, emerging at a spring somewhere downstream after a journey that began decades or centuries before. It freezes and thaws on geological schedules, responding to orbital variations that play out over tens of thousands of years. It hides. On Mars, the water hid. It did not simply vanish when the atmosphere thinned and the temperatures dropped. Water does not vanish. It transforms from liquid to ice, from ice to vapor, from vapor to space, from liquid to mineral. And in each transformation, it leaves a trace, a record, a signature that patient investigation can eventually find and read. The story of where Mars's water went is one of the most carefully reconstructed stories in planetary science, and it is still being written. New findings continue to revise and complicate the picture, adding detail to what was already a surprisingly rich account of a planet's hydrological decline. To follow the water, we have to begin at the point where things started going wrong for it. The point where the atmosphere had thinned enough that liquid water at the surface became increasingly difficult to sustain. This did not happen all at once, and it did not happen everywhere simultaneously. Mars is not a uniform world. It has enormous variations in elevation, a difference of roughly 30 kilometers between the highest points on the Tharsis volcanoes and the deepest parts of the northern lowlands. It has variations in geology, in surface composition, in the amount of solar energy received at different latitudes. And it has, or had, variations in the local conditions that determined whether liquid water could persist in a given place at a given time. In the equatorial regions, where solar heating was greatest, liquid water may have persisted the longest, at least seasonally, at least in sheltered locations like the floors of deep craters where atmospheric pressure is slightly higher and temperatures slightly warmer. In the polar regions, water froze early and stayed frozen, building up the layered ice deposits that persist to this day. In the subsurface, insulated from the cold of space by overlying rock and warmed by residual geothermal heat, liquid water may have survived long after the surface had frozen over completely, but the general direction was clear. As the atmosphere thinned, the stability of liquid water at the surface declined. The regions where liquid water could exist shrank. The seasons during which it could exist shortened. The depths to which it could penetrate the surface before freezing became shallower. And the water, responding to these changing conditions, moved. Some of it moved downward. This is perhaps the most important direction, the one with the most significant implications for both the history of Mars and the search for any surviving traces of what that history might have produced. As surface temperatures dropped and atmospheric pressure fell, the surface of Mars became increasingly hostile to liquid water. But below the surface, protected from the cold space above by meters and then tens of meters of rock and regolith, the conditions were less extreme. Geothermal heat from the slowly cooling interior continued to warm the deep subsurface. The overlying rock provided insulation. And in the deep subsurface, particularly where the rock was porous and permeable, water could persist in liquid form far longer than it could at the surface. The transition happened in stages. First, the surface water froze, creating a layer of permafrost, ground that remained continuously frozen, like the permafrost that underlies much of Siberia and northern Canada on Earth today. As the planet continued to cool, the permafrost layer deepened, pushing the liquid water table further and further underground. Eventually, on a global average, the liquid water retreated to depths of many kilometers, beyond the reach of any current rover or lander, beyond the reach of any instrument we have so far sent to Mars. But there are reasons to believe it is still there. The subsurface of Mars, insulated by kilometers of rock and potentially warmed from below by residual geothermal heat, may still harbor liquid water today, not at the surface, and not as the vast flowing hydrological system of the Noachian, but as isolated pockets of brine, possibly kilometers underground, potentially still liquid because of dissolved salts that lower the freezing point of water significantly below 0 degrees Celsius. The evidence for subsurface liquid water on modern Mars is indirect but intriguing. The most compelling comes from radar measurements made by the MARSIS instrument aboard the Mars Express spacecraft. MARSIS is a radar sounder. It sends radio waves downward through the Martian surface and measures the reflections that come back from subsurface interfaces. Different materials reflect radar waves with different intensities, and liquid water, being electrically conductive, reflects radar waves particularly strongly. In 2018, a team of researchers analyzing MARSIS data from the South Polar region of Mars announced the detection of a bright radar reflection approximately 1.5 kilometers beneath the South Polar ice cap. The reflection had the characteristic expected from a liquid water interface, the same kind of reflection produced by subglacial lakes beneath the Antarctic ice sheet on Earth, like Lake Vostok and Lake Whillans, which have been confirmed to be liquid water bodies buried beneath kilometers of ice. The interpretation of this reflection as a subglacial lake on Mars generated significant excitement and significant debate. Follow-up analyses identified additional candidate reflections in the same region, which could indicate multiple buried water bodies, or a more complex subsurface geology. Critics pointed out that the required temperatures at that depth, based on current estimates of Martian geothermal heat flow, should be too cold for even brine to remain liquid, raising questions about whether the radar reflection might have an alternative explanation, perhaps involving some unusual mineral deposit rather than liquid water. The debate continues, the data are real, the interpretation remains uncertain, but the broader point, that liquid water may still exist in the Martian subsurface, in some form, in some locations, is taken seriously by a significant portion of the Mars science community. And the implications of that possibility for the question of whether Mars might harbor surviving biology are profound, in ways we will explore in later chapters. Some of the water moved upward, not all at once, and not in large quantities, but the process of sublimation, by which ice converts directly to vapor without passing through a liquid phase, has been moving water from the Martian surface into the atmosphere throughout the planet's history. That water vapor, once in the atmosphere, can be transported by winds to other latitudes, where it may refreeze on cold surfaces or escape to space through photodissociation. The process by which ultraviolet radiation from the sun breaks water molecules apart into hydrogen and oxygen, with the lighter hydrogen then escaping the planet's gravity. This photodissociation pathway is one of the routes by which Mars has lost water to space over geological time. The hydrogen escapes, the oxygen is left behind, and some of it ends up bonded to iron minerals in the surface dust, contributing to the rust that gives Mars its color. Some of the water escaped to space directly. Early in Mars's history, when the atmosphere was thicker and water vapor was more abundant, photodissociation would have been a more significant loss mechanism. The hydrogen produced by the breakdown of water molecules, being the lightest element, escapes planetary gravity relatively easily. Over billions of years, the cumulative loss of hydrogen to space represents a loss of water. Each hydrogen atom that escapes to space is a hydrogen atom that can never recombine into a water molecule. The isotopic record confirms this. The ratio of deuterium, heavy hydrogen, with an extra neutron, to ordinary hydrogen in the Martian atmosphere is approximately 5 times higher than the same ratio in Earth's ocean water. This enrichment in heavy hydrogen is the signature of preferential loss of the lighter isotope to space over geological time. The same principle as the atmospheric isotope enrichment discussed in the previous chapter. Lighter isotopes escape more easily, leaving the remaining reservoir enriched in the heavier variants. From the magnitude of this deuterium enrichment, scientists can estimate how much water Mars has lost over its history. The numbers suggest that ancient Mars may have had enough water to cover the entire planet in a global ocean roughly 100 to 150 meters deep, though of course the water was never uniformly distributed, and much of it would have been concentrated in the northern lowlands and in the subsurface. Some of the water stayed. The polar ice caps contain significant quantities of water ice, particularly the North Polar Cap, which is primarily water ice beneath a thin seasonal veneer of frozen carbon dioxide. The South Polar Cap is more complex, with a permanent layer of carbon dioxide ice overlying a substantial reservoir of water ice. Estimates of the total water locked in the polar caps, if melted and spread uniformly over the Martian surface, suggest a global equivalent layer of approximately 35 meters, a significant amount, though far less than what the ancient Mars had. Additional water ice exists outside the polar caps, in the mid-latitude subsurface, where radar sounders and neutron spectrometers have detected significant ice deposits buried just beneath the surface. The Mars Odyssey spacecraft's neutron spectrometer mapped the distribution of hydrogen in the shallow Martian subsurface, which serves as a proxy for water ice, and found that vast regions of the mid-latitudes, covering perhaps a third of the planet's surface, contain substantial amounts of subsurface ice. This ice is not the same as the ancient liquid water that flowed in the Noachian rivers and lakes. It is the residue of a much simpler system, frozen static weighting. It preserves something of the ancient water budget, but it is a remnant, not a continuation. The water that once moved through Martian valleys and filled Martian craters now sits still beneath the surface, locked in the cold and the dark, doing nothing that water can only do when it moves. And yet, there is one more form of water on Mars that deserves mention, one that suggests the story of liquid water on Mars may not be entirely in the past. On warm summer days near the equator, when sunlight heats the dark, iron-rich surface rock and the atmospheric humidity is at its daily peak, conditions briefly exist that are close to the threshold for liquid water stability. Some researchers have proposed that thin films of liquid water, not flowing streams, not standing pools, but microscopic layers on mineral surfaces, might form transiently under these conditions, persisting for minutes or hours before evaporating or refreezing. This is not the same as the ancient rivers and lakes. It is barely water in any meaningful sense, a molecular film, invisible, present for moments on cold rock. But it raises a question about the boundary between a wet Mars and a dry one. Perhaps that boundary is not as sharp as the geological record makes it appear. Perhaps in some microscopic and intermittent way, water has never entirely left. If that is true, then the story of Mars and water is not a story with a clear ending. It is a story of transformation, from abundance to scarcity, from flowing to frozen, from surface to subsurface, from geologically active to biologically speculative. The water changed form, it moved, it hid, and some of it may be hiding still. Before we ask whether anything lived on ancient Mars, we need to ask a quieter question. What does life actually need? Not in the philosophical sense, not the poetry of what makes existence meaningful, or what separates the living from the non-living in some deep metaphysical way. In the practical, physical, chemical sense, what are the minimum requirements? What are the non-negotiable conditions that, as far as we can determine from studying life on Earth and from our theoretical understanding of chemistry and biology, must be present for life to begin and persist? This is not a simple question. It sounds like it should be. Surely we know what life needs, having lived it and studied it for centuries. But the more carefully scientists have looked at the requirements for life, the more complicated the picture has become. Not because life turns out to need more than we thought, but because it consistently turns out to need less. The story of astrobiology, the science of life in the universe, including life that may exist or may have existed beyond Earth, is largely a story of expanding definitions of habitability, of discovering that life on Earth exists in places we were certain it could not, under conditions we were confident were too extreme, using chemical pathways we did not know were possible, and of using that expanding knowledge to reassess what was once dismissed as uninhabitable. Let us start with the basics as we currently understand them. The first requirement is liquid water. Every living thing we have ever found, studied, or theorized about in any serious scientific context requires liquid water as a solvent, the medium in which the chemical reactions of life occur. Water has properties that make it uniquely suited to this role. It is liquid across a wide range of temperatures. It is an excellent solvent for a vast number of biologically important molecules. It participates directly in many of the chemical reactions of metabolism. It remains liquid under the pressures found at most planetary surfaces and in most subsurface environments. And it is abundant throughout the universe, one of the most common molecular combinations of the most common reactive elements. Could life use a different solvent? Some researchers have speculated about life based on liquid methane, liquid ammonia, or other solvents that might be stable under conditions where water is not. These ideas are scientifically interesting, but no evidence for such life has been found, and the biochemistry of alternative solvent life remains largely theoretical. For the purposes of assessing Mars specifically, where water was present in abundance, the question of alternative solvents is a fascinating digression, but not a necessary one. The second requirement is a source of energy. Life needs energy to maintain itself against the tendency toward disorder, to build complex molecules, to repair damage, to reproduce, to move. On Earth, life has found an astonishing variety of ways to obtain this energy. Photosynthesis uses sunlight directly. Chemolithotrophy, the metabolic strategy of organisms that live in deep rock, in hydrothermal vents, in acidic mine drainage, uses the chemical energy released by reaction between inorganic compounds, iron oxidation, sulfur oxidation, hydrogen oxidation, methane production. These organisms do not need sunlight. They do not need organic material from the surface. They live entirely on the chemical energy available in their immediate geological environment. This is a critically important point for Mars. If life on Mars existed, it almost certainly could not have relied on photosynthesis as its primary energy source. The early Martian surface, while perhaps habitable in other respects, would have been exposed to significant ultraviolet radiation, particularly after the magnetic field faded and the atmosphere thinned. Ultraviolet radiation is damaging to biological molecules, and a Martian surface organism would have needed either protection or an extremely efficient repair mechanism to survive it. But chemolithotrophy requires neither sunlight nor a benign surface environment. It requires only chemical gradients, differences in the oxidation state of elements that organisms can exploit to extract energy. In hydrothermal environments, where hot water laden with reduced compounds like hydrogen sulfide or hydrogen gas meets cooler, more oxidized water, these gradients are abundant and persistent. On early Mars, with its active hydrothermal systems and its water rock chemistry, such gradients would have been present. The third requirement is a set of chemical building blocks: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, along with trace amounts of other elements. These are the raw materials from which biological molecules are constructed. Carbon is the structural backbone of life as we know it. Its ability to form 4 chemical bonds simultaneously, creating chains and rings and networks of almost limitless complexity, is what makes the extraordinary chemical diversity of biology possible. All of these elements are present on Mars. Carbon is in the atmosphere as carbon dioxide and in carbonate minerals in the rocks. Hydrogen is in water. Nitrogen has been detected in the Martian atmosphere. Oxygen is everywhere, bound up in minerals and in the thin atmospheric carbon dioxide. Phosphorus and sulfur have both been detected in Martian rocks and soils. The chemistry of life is not exotic. It uses the most common reactive elements in the universe. Finding those elements on Mars is not surprising, and their presence alone tells us nothing definitive about whether life arose there. But their absence would have been decisive evidence against it, and they are not absent. The fourth requirement, less often stated but increasingly recognized, is time. Life does not appear instantaneously. On Earth, the earliest evidence for life, carbon isotope signatures in ancient rocks, dates to perhaps 3.7 to 4 billion years ago, within a few hundred million years of the formation of the planet. But the gap between a planet having the right chemical ingredients and liquid water, and that planet having self-replicating biochemical systems, is not understood. We do not know how long the origin of life takes. We have exactly one example. The sample size is too small to draw statistical conclusions. What we can say is that life on Earth appeared relatively quickly by geological standards, quickly enough that some researchers have argued it may not be an extraordinarily improbable event, but rather a fairly reliable consequence of the right conditions being maintained for a sufficient period. Ancient Mars had liquid water for perhaps 1 billion years. It had the chemical building blocks. It had energy sources in the form of hydrothermal gradients and volcanic chemistry. It had time, not as much time as Earth has had, and perhaps not under continuously optimal conditions, but substantial time nonetheless. The question is not whether Mars had the conditions that life requires. The evidence suggests that it did, at least in the broad sense, at least in certain environments, at least during the Noachian period. The question is whether the conditions were right in the right way, in the right place, for the right duration. And that is a much harder question. There are researchers who approach the origin of life as a problem of chemistry, a question of whether the right reactions can occur under the right conditions, given enough time. In this view, life is something like an inevitable outcome of certain chemical environments. Warm water, chemical gradients, organic molecules, time, and eventually perhaps self-replicating chemistry emerges, because that is simply what chemistry does in certain configurations. If this view is correct, then ancient Mars, with its hydrothermal systems and its billion-year window of habitable conditions, was a very good candidate for life. There are other researchers who see the origin of life as something more contingent, a sequence of improbable steps, each requiring specific conditions and a degree of good fortune, such that most habitable planets will never actually produce life, even if they maintain habitable conditions for billions of years. If this view is correct, then even a Mars with perfect conditions might never have crossed the threshold into biology. We do not know which view is correct. We have not yet found life beyond Earth, and we have not yet fully understood how life arose on Earth in the first place. The origin of life remains one of the deepest unsolved problems in all of science. But here is what we can say with confidence. If life were to exist anywhere beyond Earth in our solar system, if there were a place, other than our own planet, where the conditions for life were met, where the chemical building blocks were present, where the energy sources were available, where the liquid water was there, ancient Mars would be a strong candidate. Not a certain one, not even perhaps the most likely one among the candidates in our solar system, but a strong candidate. A world that for a meaningful span of geological time checked the boxes that we believe matter. And the universe, as best we can tell, does not leave many check boxes unchecked for long. Every door has a threshold, not in the poetic sense only, but in the physical one. A threshold is the moment when conditions on one side become conditions on the other side, when the temperature crosses from below freezing to above, when the pressure rises from too low to sustain liquid water to just sufficient, when the chemistry shifts from sterile to potentially productive. A threshold is where one state of affairs ends and another begins. For life on Mars, if it ever existed, there was a window. A period of time during which the conditions were on the right side of enough thresholds simultaneously. When water was liquid, when chemistry was active, when energy was available, when the environment was not so hostile that any emerging complexity would be immediately destroyed. A period when the door was open. Understanding that window, how wide it was, how long it lasted, how stable it was, and what was happening inside it is one of the central questions of Mars astrobiology. And the answer, as is with most things about Mars, is more complicated and more interesting than it first appears. The broad outlines of the window are reasonably well established. The most favorable period for life on Mars was the Noachian epoch, roughly 4 billion to 3.5 billion years ago. This is the period when liquid water was most abundant at the surface, when volcanic activity was most intense, when hydrothermal systems were most widespread, when the atmosphere was thickest and the greenhouse warming most effective. This is the period recorded in the ancient, heavily cratered southern highlands. The old terrain that preserves the mineral signatures, the valley networks, the lake sediments, the delta deposits that tell us Mars was once genuinely wet. 1 billion years. Perhaps somewhat less, perhaps somewhat more, depending on which region of Mars you are considering and how strictly you define habitable conditions. But on the order of 1 billion years during which Mars had, in at least some locations, the conditions that life requires. 1 billion years is difficult to feel the weight of. Consider that complex animal life on Earth. Organisms with multiple cells, with organs, with movement, with something resembling behavior, only appeared about 600 million years ago. 1 billion years of Martian habitability is longer than the entire history of complex animal life on our own planet. It is longer than the time that has passed since the Cambrian explosion, the event that produced most of the major animal body plans that exist today. In 1 billion years on Earth, a great deal can happen. Single-celled life can evolve into multicellular life. Metabolic strategies can diversify, ecosystems can develop, species can arise, flourish, diversify, and go extinct. The history of life on Earth across an equivalent span, from roughly 2 billion years ago to 1 billion years ago, encompasses the development of eukaryotic cells, the acquisition of mitochondria through endosymbiosis, the beginning of sexual reproduction, the first evidence of multicellular organisms, an enormous amount of biological innovation, compressed into a single billion-year chapter. We do not know whether 1 billion years of Martian habitability was enough time for anything comparable to happen there. We do not know whether the habitability was continuous enough, stable enough, chemically rich enough to allow the kind of sustained biological development that happened on Earth. The Martian window may have been more intermittent than the word habitability implies. Periods of warmth and liquid water separated by cold, dry intervals, during which any emerging life would have had to survive in sheltered niches or in the subsurface. But intermittent habitability is not the same as no habitability. Some of the most resilient organisms on Earth, extremophiles, the technical term for organisms that thrive under conditions once thought to be incompatible with life, are specifically adapted to intermittent environments. Tardigrades, the microscopic animals sometimes called water bears, can survive complete desiccation, extreme radiation, and temperature ranges from near absolute zero to above 150 degrees Celsius by entering a state of suspended animation called cryptobiosis when conditions become intolerable and resuming activity when conditions improve. Certain bacteria form endospores, tough, dormant structures that can survive in a dormant state for millions of years, and return to active life when moisture and nutrients become available. Certain algae and cyanobacteria survive in the dry valleys of Antarctica by living inside porous rocks, where thin films of liquid water form briefly during the warmest days of the austral summer. These organisms did not arrive pre-adapted to their extreme environments. They evolved those adaptations over long periods in gradually changing conditions, each generation pushing slightly further into the extreme. If life arose on Mars during the wet Noachian period, it would have had hundreds of millions of years of slowly deteriorating conditions, during which to develop exactly these kinds of adaptations, to become more resistant to desiccation, to radiation, to cold, to the increasingly sparse chemical energy available in a drying world. In this scenario, Martian life would not have simply died when the surface water disappeared. It would have retreated. It would have followed the water downward, into the subsurface, where liquid water persisted longer. It would have evolved to survive on less water, less energy, less chemical complexity. It would have become, over hundreds of millions of years, the kind of hardy, minimal, deeply buried organism that we have only recently begun to discover in the deep subsurface of Earth. We have found life kilometers underground on Earth. We have found bacteria living in ancient rock fractures, surviving on the hydrogen produced by the slow reaction of water with iron-bearing minerals, a reaction so slow, and the energy it produces so meager, that the organisms living on it divide perhaps once every 10,000 years. Not 10 years, not 1,000 years, 10,000 years between cell divisions. These are organisms so far removed from the active, energetic life we see at the surface that they represent almost a different concept of what living means. If anything like this ever existed on Mars, if life arose during the Noachian and retreated gradually into the deep, cold subsurface as the surface dried, it might, in principle, still be there. Not flourishing, not active in any meaningful sense, but persisting, dividing once every geological age, waiting, in the way that deeply buried things wait, for conditions that may never return. This is one end of the spectrum of possibilities. The other end is equally important to acknowledge. The window of Martian habitability, while real and significant, also had characteristics that may have made it less productive for life than the Noachian record alone suggests. Mars's habitability was likely episodic rather than continuous, even during the Noachian. The climate models that struggle to warm ancient Mars consistently enough for permanent surface liquid water may be telling us something real, that the ancient Martian surface was, on average, cold and frozen, with liquid water appearing episodically during volcanically active periods, large impact events, or favorable orbital configurations. If liquid water was present for millions of years, but in bursts separated by frozen intervals, the continuity of any emerging chemistry would have been interrupted repeatedly. The origin of life may require continuous, stable conditions over a long period, a sustained chemical environment in which increasingly complex molecular systems can develop without being destroyed and starting over. If the Martian environment was repeatedly frozen and thawed, each warm period may not have built productively on the last. The chemistry may have been reset each time. Additionally, the early Martian surface, while wet, was also exposed to intense ultraviolet radiation during the period after the magnetic field faded and before the atmosphere thinned enough to reduce the solar input. The surface may have been simultaneously habitable in terms of water availability and hostile in terms of radiation. Life would have needed to be underground or protected by meters of rock or ice to survive. And there is the transition itself, the shift from the warm, wet Noachian to the cold, dry Hesperian. Even if life had arisen and established itself during the favorable early period, the speed of the environmental deterioration relative to the pace of biological adaptation may have outrun whatever was there. If conditions deteriorated faster than organisms could adapt, even a biologically productive early Mars could have ended up lifeless. We do not know the rate of that deterioration in detail. We do not know how quickly the transition from the Noachian to the Hesperian happened in specific regions, or how much variation there was across the planet. Some areas may have remained habitable long after others had dried out. The heterogeneity of the Martian surface suggests that the window of habitability was not a single, uniform period, but a patchwork of local histories, some locations remaining wet and warm for much longer than others. Jezero Crater, with its delta deposit and its ancient lakebed sediments, represents one such location, a place where habitable conditions persisted long enough to accumulate significant sedimentary records. The samples being collected there by Perseverance are in a sense samples from inside the window. They are the most direct available record of the conditions that existed during the period when Mars was most likely to have been alive. When those samples return to Earth, if the sample return mission proceeds as planned, sometime in the mid-2030s, They will be analyzed with instruments of extraordinary sensitivity, looking for chemical, isotopic, and possibly morphological evidence of ancient biology. The results of those analyses will not definitively answer the question of life on Mars either way, but they will narrow the range of possibilities in ways that no remote measurement from orbit or rover can accomplish. The window of Martian habitability is not just a chapter in the planet's geological history. It is a question addressed to the universe. A question about whether life is common or rare, about whether the right conditions reliably produce the right outcomes, about whether the billion-year window that Mars kept open, warm enough, wet enough, chemically rich enough, was enough. We are still waiting for the answer. There is a particular kind of patience that science requires. Not the patience of waiting for something to happen, though that is part of it. Something deeper. The patience of looking carefully at something that may contain an answer, knowing that the answer may not be there, knowing that the looking itself may take years or decades, and choosing to look anyway. Choosing to design the instruments, build the spacecraft, wait out the years of interplanetary travel, land on a surface no human foot has touched, drive slowly across ancient rock, and collect samples from a world that has been silent for 3 billion years. This is what Mars exploration has required, and what it has returned so far is not a definitive answer. It is something more interesting, a growing body of evidence that is, piece by piece, narrowing the space of possibilities without yet closing it. Let us take stock of what we actually know. The first thing to say is that no Mars mission has found direct, confirmed evidence of life, past or present. This is the honest starting point. There is no photograph of a Martian organism. There is no biological sample returning from Mars with cell walls intact or DNA sequences readable. There is no confirmed chemical signature that can only be explained by biology and cannot be explained by abiotic chemistry. That is the reality of where we are. But the absence of confirmed life is not the same as evidence against it. And the evidence that has accumulated, indirect, ambiguous, incomplete, but genuine, has consistently pushed in a direction that keeps the question open rather than closing it. Begin with the organic molecules. In 2018, NASA's Curiosity rover announced one of its most significant findings from its long traverse of Gale Crater. The rover had detected organic molecules, carbon-containing compounds, preserved in ancient mudstone rock more than 3 billion years old. Specifically, it found thiophene, methanethiol dimethyl sulfide, and other sulfur-bearing organic compounds, along with fragments of larger organic molecules, in rock samples drilled from the ancient lakebed sediments. Organic molecules are not by themselves evidence of life. The word organic in chemistry simply means carbon-containing. It does not imply biological origin. Organic molecules form through purely chemical processes in many environments, including in space, where they are found in meteorites, comets, and interstellar clouds. The solar system is rich in organic chemistry that has nothing to do with biology. But finding organic molecules preserved in 3 billion-year-old Martian rock is still significant for 2 reasons. First, it demonstrates that organic molecules can survive on Mars across geological timescales. Mars's surface is bombarded by ultraviolet radiation and by oxidizing chemicals in the soil, conditions that tend to destroy organic molecules relatively quickly. Finding complex organics preserved in ancient rock shows that the geological environment can protect organic material from these destructive processes, at least when it is buried and sheltered from the surface. If life ever existed on Mars and left behind organic traces, those traces could in principle have been preserved in a similar way. Second, the specific molecules found are consistent with what you would expect from the breakdown of more complex organic compounds over geological time. They are fragments, degradation products. They suggest the presence of more complex organic chemistry in the original ancient rock that has been partially destroyed by 3 billion years of radiation and oxidation. What we are seeing in the Curiosity data may be the remnants of a richer organic chemistry that existed in the ancient Martian lakebed. A chemistry that could have been biological in origin, or could have been entirely abiotic, but that was, in either case, more complex and more interesting than the current Martian surface would suggest. Then there is the methane. Methane is a simple organic molecule, 1 carbon atom bonded to 4 hydrogen atoms. It is significant in the context of Mars for one specific reason. On Mars, in the presence of ultraviolet radiation and the oxidizing chemistry of the Martian atmosphere, methane is destroyed relatively quickly. By some estimates, methane molecules in the Martian atmosphere should survive for only a few hundred years before being broken down. If methane is present in the Martian atmosphere, something must be producing it on a timescale comparable to the rate of its destruction. On Earth, the vast majority of atmospheric methane, about 90%, is biological in origin. is produced by methanogenic archaea, single-celled organisms that generate methane as a metabolic byproduct in oxygen-poor environments, like the digestive systems of ruminants, rice paddies, and wetland sediments. Methane is, in this sense, one of the most robust biosignatures on Earth, one of the clearest chemical signals of biological activity in the planetary atmosphere. There is also geological methane, produced by the reaction of water with certain iron and magnesium silicate minerals in a process called serpentinization, or released from geological deposits. Methane does not require life to be produced. But when Curiosity detected methane in the Martian atmosphere, measuring concentrations that varied with the seasons, rising in summer and falling in winter, with occasional spikes that suggested local sources, the result attracted enormous attention. And when the European Space Agency's Mars Express orbiter independently detected a methane spike in 2004 that coincided with Curiosity's measurement from the surface during a later period, the evidence for variable, seasonally cycling methane became harder to dismiss. What is producing the methane? The honest answer is that we do not know. The most straightforward geological explanation involves serpentinization, the reaction of water with olivine-rich rock that produces hydrogen and, in certain conditions, methane. Mars has abundant olivine, and the subsurface, where water may still exist in some form, could in principle support this reaction today. This is a serious, well-supported abiotic explanation, but a biological explanation cannot be ruled out. If methanogenic microorganisms persist in the Martian subsurface, in the deep, potentially liquid, chemical environments that have been insulated from the surface for billions of years, they could be producing methane in the same way that their counterparts on Earth produce it. The seasonal variation observed by Curiosity, more methane in summer, less in winter, could reflect temperature-dependent changes in microbial activity, or it could reflect temperature-dependent changes in the physical processes that release geologically produced methane from the subsurface. Both explanations are physically plausible. Neither has been definitively confirmed or ruled out. There is also the question of the Martian surface chemistry more broadly. The Viking landers of the 1970s, the first spacecraft to successfully land and operate on the Martian surface, carried a biology experiment specifically designed to test for metabolic activity in the Martian soil. The results were ambiguous in a way that has generated scientific debate for 50 years. One of the experiments, the labeled release experiment, which added a nutrient solution to a sample of Martian soil and measured whether any gas was produced, as it would be by metabolizing organisms, gave a positive result. Gas was produced. The soil was reacting to the nutrient solution in a way that resembled biological metabolism. But the other Viking biology experiments did not support a biological interpretation, and a subsequent analysis of the Martian soil by a different Viking instrument found no organic molecules, a result that at the time was taken as strong evidence against biology, since living organisms produce organic molecules. The positive labeled release result was eventually attributed by most researchers to the chemistry of reactive compounds in the Martian soil, specifically hydrogen peroxide or perchlorates, which are known to exist in the Martian surface and which can drive oxidative reactions that resemble, but are not, biological activity. This explanation is generally accepted, but not without reservation. The scientist who designed the labeled release experiment, Gilbert Levin, maintained until his death in 2021 that the Viking results should be interpreted as evidence of biological activity, and that the non-biological explanation has never been entirely satisfying. The debate, settled in the minds of most researchers, was never fully settled in his. What does all of this add up to? Organic molecules preserved in ancient rock, variable atmospheric methane of uncertain origin, ancient habitable environments confirmed by mineralogy and sedimentology, subsurface environments where liquid water may persist today, a Viking biology experiment whose results have never been unambiguously explained. It is not evidence of life. It is not even close to a confirmation. But it is a collection of open questions, each one individually explainable without biology, but collectively forming a portrait of a planet that is not yet fully understood. A planet that keeps producing results that require investigation rather than dismissal. A planet that has so far declined to give us a clear negative result. In science, a clear negative result is itself valuable. It closes a door, it narrows the search space. It tells you where not to look next time. Mars has not given us that clear negative. And until it does, the question of whether something once lived in its ancient lakes and hydrothermal systems or still persists in its cold, dark, deep subsurface remains genuinely open.